Right now, at this very moment, a beam of light is racing through the void at 299,792,458 meters per second. Nothing in the known universe moves faster. It is the absolute speed limit of reality itself, a boundary etched into the equations that govern everything from atoms to galaxies. And yet, if you aimed that beam of light toward the edge of the observable universe, it would never arrive, not in a million years, not in a billion, not even. If the universe lasted forever, that is not an exaggeration, it is not a metaphor, it is the measured, verified, mathematically certain consequence of living in a cosmos that is expanding faster than light can cross it. That fact alone should stop you cold. We live inside a sphere of visibility. Everything we have ever observed, every star, every galaxy, every faint whisper of radiation, from the earliest moments of cosmic history, it all exists within a bubble roughly 93 billion light-years across. That number deserves a moment of silence. 93 billion light-years. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. Multiply that by 93 billion, and you get a distance so vast that the human brain cannot process it. We can write it down, we can perform calculations with it, but we cannot feel it. Our minds evolved to estimate the distance to a tree or a river, not the diameter of creation. The observable universe is not merely large, it is large in a way that breaks the very concept of largeness. And here is the first unsettling truth. The observable universe is not the whole universe. It is merely the part we can see. The word observable is doing extraordinary work in that phrase. It means the region from which light has had enough time since the beginning of everything to reach us. Beyond that boundary there could be more space, more galaxies, more of everything, stretching out perhaps without limit, perhaps forever. We do not know what lies beyond. We may never know. The light from those regions has not had time to reach us. Given the accelerating expansion of space, it never will. Now consider what it would mean to travel to that boundary. Not at walking speed, not at the speed of an aeroplane, not even at the speed of our fastest spacecraft, which can manage roughly 600,000 kilometers per hour. Consider what it would mean to travel at the speed of light itself. You would need to move at roughly 1.08 billion kilometers per hour every second of every day, without slowing, without stopping, without resting. And even at that impossible velocity, even harnessing the fastest phenomenon the universe permits, the journey would take longer than the current age of the cosmos. Far longer. Because the edge of the observable universe is not standing still. It is moving away from us, and it is moving away faster than light itself can travel. The universe is approximately 13.8 billion years old. The edge of the observable universe sits more than 46 billion light-years away in every direction. That gap, that enormous mismatch between the age of the universe and the distance to its visible edge, is one of the most profound puzzles in all of cosmology. It tells us something extraordinary and deeply counterintuitive. Space itself has been stretching. The fabric of the cosmos has been expanding, pulling everything apart, and it has been doing so since the first instant of existence. The expansion is not slowing down, it is speeding up. And the further away something is, the faster it recedes. At the edge of the observable universe, the recession speed is many times faster than light. So the question is not simply how long the journey would take. The question is whether the journey is even possible in principle. Whether any traveler, no matter how advanced, no matter how powerful their technology, no matter how much time they had, could ever reach a destination that is running away from them faster than they can chase it. The answer, it turns out, is deeply unsettling. It touches the very nature of space, time, and what it means to exist in a universe that is not merely large, but actively, ceaselessly expanding. By the end of tonight, you're going to understand why the edge of the observable universe is not just far away but fundamentally unreachable. You are going to understand what that means for every civilization that has ever existed or ever will exist. And you are going to confront a truth about our cosmic isolation that most people have never considered. It is a truth that does not require advanced physics to feel. It only requires a willingness to sit with the scale of the cosmos and let it settle into your bones. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The universe is not what it appears to be. It is stranger, larger, and more indifferent than any human mind was built to comprehend. The distances involved are not merely inconvenient. They are barriers woven into the fabric of reality itself, consequences of the same physical laws that allow stars to shine and atoms to exist. And the further we look, the more we realize that the cosmos has placed a hard limit on how much of itself it will ever allow us to touch. We are not explorers in an open frontier. We are observers, peering through a window that is slowly, irreversibly closing. The night sky, which seems so permanent, so eternal in its scattering of stars, is in fact a snapshot of a vanishing moment. The galaxies we see tonight are further away than they were last night. Tomorrow they will be further still, and some of them, the most distant, the faintest, will one day vanish entirely, their light stretched beyond detection, their existence erased from our view. The universe is not only vast, it is leaving. Now, let's begin. To understand why reaching the edge of the observable universe is such a staggering proposition, we first need to understand what we mean by distance in the cosmos. Because distance, at the scale of the universe, does not behave the way our everyday experience suggests. On Earth, distance is fixed. The space between two cities does not grow while you drive between them. The road does not stretch beneath your wheels. The gap between your house and the grocery store is the same whether you measure it on Monday or on Friday. But in the universe, that is precisely what does not happen. The space between objects is growing, and it has been growing since the very beginning of time itself. The story begins with a Belgian priest and physicist named Georges Lemaitre. In 1927, Lemaitre proposed something radical. He suggested that the universe was not static, not eternal and unchanging, as most scientists of his era believed. Albert Einstein himself had added a term to his own equations, a so-called cosmological constant, specifically to prevent them from predicting an expanding or contracting universe. Einstein believed, as most people did in the early 20th century, that the universe was steady and eternal. But Lemaitre looked at the same equations and saw something different. He saw a cosmos in motion. He argued that the universe was expanding, that it had started from a single primordial point, a state of unimaginable density and heat, and had been growing ever since. He called this original state the primeval atom. Today, we call it the Big Bang. 2 years later, in 1929, the American astronomer Edwin Hubble provided the observational evidence. Hubble had been studying distant galaxies using the 100-inch Hooker telescope at Mount Wilson Observatory in California, at the time the largest telescope in the world. He noticed something strange. Nearly every galaxy he observed was moving away from us. The light from those galaxies was stretched toward the red end of the spectrum, a phenomenon called redshift. When a source of light moves away from an observer, the wavelengths of the light are stretched, shifting the light toward lower frequencies. For visible light, this means shifting toward the red end of the rainbow. The further away a galaxy was, the more its light was redshifted, meaning the faster it appeared to be moving away. It is worth noting that Hubble's work built on earlier observations by Vesto Slipher, an astronomer at the Lowell Observatory in Arizona. As early as 1912, Slipher had begun measuring the redshifts of what were then called spiral nebulae, objects we now know to be distant galaxies. By 1917, Slipher had measured the velocities of 25 such nebulae and found that all but 4 were moving away from us. His data hinted strongly at a universe in motion, though the full interpretation required the theoretical framework that Lemaitre and Hubble would provide. Science rarely progresses through a single flash of insight. It is built brick by brick, observation by observation, across decades and careers. Hubble's key contribution was not merely measuring redshifts but combining them with distances. To measure how far away each galaxy was, Hubble used a class of pulsating stars called Cepheid variables, whose brightness varies in a predictable pattern. The astronomer Henrietta Swan Leavitt had discovered in 1908 that the period of a Cepheid's brightness variation is directly related to its intrinsic brightness. By measuring the period, you can determine how bright the star truly is. By comparing that to how bright it appears, you can calculate its distance. This technique, called the distance ladder, remains one of the most important tools in astronomy. Hubble used Cepheids in nearby galaxies to calibrate the distances, then extended the calibration to more distant objects using other methods. The result was clear. Recession speed increased with distance. The universe was expanding. This was not because the galaxies were flying through space like shrapnel from an explosion. It was because the space between us and those galaxies was expanding. Every point in the universe was moving away from every other point, not because objects were hurtling outward from a center, but because the fabric of space itself was growing. Imagine dots painted on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is at the center. The expansion is happening everywhere, uniformly. That is the expanding universe. This relationship between distance and recession speed became known as Hubble's law, though it is now often called the Hubble-Lemaitre law to honor Lemaitre's earlier theoretical prediction. The law states that the velocity at which a galaxy recedes from us is proportional to its distance. The constant of proportionality is called the Hubble constant, usually denoted h0. The current best estimate for this value, derived from observations by the European Space Agency's Planck satellite and other instruments, is approximately 67.4 kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light-years, or roughly 10.6 million trillion kilometers. So for every additional 3.26 million light-years of distance between us and a galaxy, that galaxy appears to be receding at an additional 67.4 kilometers per second. At modest distances, this expansion is negligible. A galaxy 5 million light-years away is receding at roughly 103 kilometers per second. You would not notice this in everyday life. But across billions of light-years, the numbers become enormous. A galaxy 1 billion light-years away is receding at roughly 20,000 kilometers per second. A galaxy 10 billion light-years away is receding at roughly 200,000 kilometers per second, which is more than half the speed of light. And at the extreme distances near the edge of the observable universe, recession velocities exceed the speed of light many times over. Let us now build a visceral sense of scale, because without it, the numbers we have been discussing are just abstractions. They float through the mind without leaving a mark. We need to anchor them to something tangible. Start with something familiar. The Earth is roughly 12,742 kilometers in diameter. You can fly around the entire planet in about 40 hours on a commercial airplane. That is a distance our minds can handle. Now, zoom out. The Moon orbits the Earth at an average distance of about 384,000 kilometers. Light covers that distance in roughly 1.3 seconds. When astronauts traveled to the Moon during the Apollo missions, the journey took about 3 days each way. That is the furthest any human being has ever traveled from Earth. Now zoom out further. The Sun is approximately 150 million kilometers from Earth. Light takes about 8 minutes and 20 seconds to cross that gap. At highway speed, roughly 100 kilometers per hour, the drive to the Sun would take roughly 171 years, a human lifetime, non-stop, no breaks, and you still would not arrive. Zoom out again. The planet Neptune, the most distant major planet in our solar system, orbits the Sun at an average distance of about 4.5 billion kilometers. Light takes roughly 4 hours and 10 minutes to reach Neptune from the Sunday. The Voyager 2 spacecraft, launched in 1977, took 12 years to reach Neptune, arriving in 1989. Now make the leap to interstellar space. The nearest star to our Sun is Proxima Centauri, a small red dwarf star in the Alpha Centauri system. It sits 4.24 light-years away. That means light, traveling at its maximum speed, takes more than 4 years to cross the gap. If you were to drive a car at 100 kilometers per hour, 24 hours a day, without ever stopping, it would take you roughly 46 million years to reach Proxima Centauri. 46 million years. The age of the dinosaurs was roughly 66 million years ago. You would need to drive for nearly as long as it has been since the extinction of the dinosaurs just to reach the nearest star, and that is the closest one. The Milky Way contains between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. Here is where the first scaled comparison becomes essential. If you could shrink the entire observable universe down to the size of Earth, our entire Milky Way galaxy would be smaller than a single grain of sand. Not a beach ball, not a marble, not even a pebble, a grain of sand. The Milky Way, a galaxy containing hundreds of billions of stars, stretching 100,000 light-years from one spiral arm to the other, home to every star and planet and civilization that has ever been visible from our night sky, would be an almost invisible speck inside this Earth-sized model of the observable universe. There would be roughly 2 trillion such grains, each representing a galaxy, scattered throughout this model Earth. The distances between grains would be vast relative to their size, as though you scattered 2 trillion grains of sand inside a sphere the size of our planet, leaving enormous empty spaces between them. Here is another way to feel the scale. Imagine the Sun is the size of a basketball, roughly 24 centimeters in diameter. At that scale, the Earth would be a tiny bead about 2.3 millimeters across, sitting roughly 26 meters away. Jupiter would be about the size of a large marble, roughly 2.6 centimeters, orbiting at about 140 meters from the basketball sundae. Neptune would be a small pea circling at roughly 760 meters. And the nearest star, Proxima Centauri, would be another basketball sitting approximately 6,400 kilometers away. That is roughly the distance from London to New York. 2 basketballs, separated by the width of the Atlantic Ocean, and that is merely the nearest star. To place the edge of the observable universe in this model, you would need to extend the scale far beyond anything earthbound. The galaxy itself, in this basketball model, would be enormous, and the observable universe would span a volume that stretches far past the orbit of the real Pluto around the real sundae. The analogy breaks apart. No single Earth-based comparison can hold the full scale. One more. If the entire history of the universe, from the Big Bang to today, were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1st and the present moment falling at midnight on December 31st, then all of recorded human history, everything from the earliest cave paintings to the present day, would occupy the last 14 seconds of the year, 14 seconds out of an entire year. The age of the dinosaurs would begin around December 25th. The formation of the Earth would happen around September 1st. For the first 8 months of this cosmic calendar, there would be no solar system, no Earth, no life of any kind in our corner of the cosmos. We arrived in the final heartbeat of cosmic time. These comparisons are not decorations. They are necessary. Without them, the numbers we have been discussing remain sterile, disconnected from anything we can feel. The human mind needs anchors, familiar objects to attach to unfamiliar magnitudes. And even with these anchors, the true scale remains elusive. We can point toward it, we can gesture in its direction, but we cannot fully grasp it. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies, 700 sextillion stars, and it is mostly, overwhelmingly, empty. The average density of matter in the cosmos is roughly 5.9 protons per cubic meter. To give you a sense of what that means, the best vacuum chambers on Earth, in which scientists create conditions as empty as possible, contain roughly 10 billion molecules per cubic meter. The average density of the universe is trillions of times emptier than the best vacuum we can produce on Earth. Space is, by any meaningful definition, nothing, punctuated by rare, scattered islands of something. Now let us talk about the cosmic microwave background, because it is central to understanding both the observable universe and the journey we are contemplating. The CMB is the oldest light in the universe. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey. They had been trying to eliminate a persistent noise from their horn antenna, a faint hiss that seemed to come from every direction in the sky with equal intensity. They checked for pigeon droppings, equipment malfunctions, atmospheric interference, and radio noise from nearby New York City. Nothing worked. The hiss persisted. Eventually, they learned that a group of physicists at Princeton University, led by Robert Dicke and Jim Peebles, had been predicting exactly such a signal. Dickey's team had realized that if the Big Bang really happened, then the early universe would have been a hot, dense fireball, and the afterglow of that fireball should still be detectable as a faint microwave radiation filling all of space. Penzias and Wilson had found it without knowing what it was. Their accidental discovery won them the Nobel Prize in Physics in 1978. The CMB tells us something remarkable about the early universe. It is a snapshot of the cosmos as it existed roughly 380,000 years after the Big Bang, a moment called recombination. Before recombination, the universe was a hot, dense plasma of protons, electrons, and photons, all tangled together in a seething fog. Photons could not travel freely because they were constantly scattered by free electrons. The universe was opaque, like the inside of a dense cloud. But as the universe expanded and cooled, the temperature dropped below about 3,000 degrees Kelvin, roughly 2,700 degrees Celsius. At that point, protons and electrons combined to form neutral hydrogen atoms. The fog cleared. Photons were suddenly free to travel through space without being scattered, and they have been traveling ever since, for 13.8 billion years, carrying information about the state of the universe at that distant moment. The temperature of that primordial radiation, when it was emitted, was approximately 3,000 degrees Kelvin. Today, after being stretched by 13.8 billion years of cosmic expansion, it has cooled to a mere 2.725 degrees above absolute zero. That is negative 270.425 degrees Celsius. The once searing light of the young universe has been redshifted from visible light all the way down to microwaves, electromagnetic radiation with wavelengths of about 1 to 2 millimeters. This is the cosmic microwave background. It fills all of space. It comes from every direction. It is the most ancient light that will ever reach our instruments. The surface from which the CMB was emitted is called the last scattering surface. At the time of emission, the matter that produced the CMB was only about 42 million light-years from the matter that would eventually become our solar system. But expansion has been stretching the space between us ever since. Today, that matter sits approximately 46.1 billion light-years away. This surface effectively marks the boundary of the observable universe. We cannot see beyond it, because the universe before that epoch was opaque. No electromagnetic radiation from earlier times can reach us. Measurements of the CMB have been refined dramatically over the decades. The Cosmic Background Explorer, or COBE, launched in 1989, confirmed that the CMB has a perfect blackbody spectrum and detected tiny temperature variations of about 1 part in 100,000 across the sky. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped those variations in much greater detail. And the European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most precise full-sky map of the CMB ever made. These tiny variations, these minute differences in temperature from one direction to another, are the seeds of all cosmic structure. They are the density fluctuations in the early universe that, under the pull of gravity, grew over billions of years into the galaxies, galaxy clusters, and cosmic filaments we see today. The Hubble Ultra Deep Field provides another window into the scale of the cosmos. This image was captured by the Hubble Space Telescope over a period of several hundred hours between 2003 and 2004. The telescope stared at a tiny, seemingly empty patch of sky roughly 1/13 millionth of the total sky area. This patch was so small you could cover it with a grain of sand held at arm's length. What emerged from that apparently blank speck was astonishing. The image revealed approximately 10,000 galaxies, ranging from nearby spirals with clearly visible arms to faint red smudges that existed when the universe was only a few 100 million years old. 10,000 galaxies, hiding behind a grain of sand. If the entire sky contained galaxies at similar density, the total number would be in the hundreds of billions. The James Webb Space Telescope, launched on December 25, 2021, has extended our view even further. JWST is an infrared observatory with a 6.5-meter primary mirror, the largest mirror ever sent into space. It orbits the Sun at a point called the second Lagrange point, roughly 1.5 million kilometers from Earth. In its first years of operation, JWST has detected galaxies that appear to have formed within 200 million years of the Big Bang, much earlier than many models predicted. Some of these galaxies are surprisingly massive for their age, challenging our understanding of how quickly the first structures in the universe could have assembled. The light from these objects has been traveling for over 13.4 billion years. By the time it reaches JWST's mirrors, the galaxies that emitted it are more than 30 billion light-years away, carried to that distance by the expansion of space. We are seeing them as they were in the infancy of the cosmos, but they now exist, if they still exist at all, at distances we cannot fathom. More recent estimates, incorporating data from the Hubble Space Telescope, the James Webb Space Telescope, and ground-based surveys, suggest the observable universe contains at least 2 trillion galaxies. 2 trillion. That number, 2 followed by 12 zeros, is difficult to comprehend even as a written figure. Each galaxy contains, on average, 100 billion to 400 billion stars. The total number of stars in the observable universe is estimated at roughly 700 sextillion, that is, 7 followed by 23 zeros. It is more than the number of grains of sand on every beach on planet Earth. This comparison has been made rigorously, and the stars win by a comfortable margin. And yet, for all those galaxies, for all those stars, the universe is overwhelmingly empty. The cosmos is a cathedral of nothing. Matter is the exception, not the rule. If you picked a random point in the observable universe, the probability that it would be inside a star or a planet or any solid object at all is vanishingly small. You would almost certainly find yourself in the void between galaxies, surrounded by darkness and near-perfect vacuum, with the nearest significant concentration of matter millions of light-years away in every direction. The temperature of that void would be just barely above absolute zero, roughly 2.7 degrees Kelvin, warmed only by the fading glow of the cosmic microwave background. That is the default state of the universe. Emptiness, cold, silence. Everything we think of as real, as solid, as important, exists in tiny, scattered pockets of complexity, adrift in an ocean of nothing. Now let us address what lies beyond the observable universe, because this matters deeply for our question. The observable universe is not the whole universe. It is merely the part from which light has had time to reach us. Think of it like standing on a ship in the middle of a vast ocean. You can see to the horizon in every direction. But the ocean does not end at the horizon. It continues far beyond your line of sight. The horizon is a limitation of your position, not a boundary of the water. The cosmic horizon works in a similar way, except that instead of being limited by the curvature of the Earth, we are limited by the finite speed of light and the finite age of the universe. The ocean of the cosmos extends beyond our horizon, perhaps to infinity. Beyond the CMB horizon, beyond the 46.5 billion light-year radius, the universe almost certainly continues. General relativity and the latest cosmological data, particularly the observed flatness of space, suggest the total universe could be far larger than the observable portion. Some estimates, based on measurements of the curvature of space by the Planck satellite, suggest the total universe could be at least 250 times larger in diameter than the observable portion. Other estimates suggest it could be infinite. We do not know. We may never know. And this uncertainty is not a temporary gap in our knowledge, waiting to be filled by better instruments. It may be a permanent feature of our existence, an inherent limit built into the structure of spacetime. The expansion of space ensures that regions beyond a certain distance are forever out of reach. They are causally disconnected from us. No signal we send will ever reach them. No signal they send will ever reach us. We are separated not by empty space, but by the growth of space, a process that is happening everywhere, at every moment, with increasing speed. These regions are not hidden behind a wall. There is no edge, no barrier, no membrane separating us from the rest of the cosmos. They are simply too far away, and getting further away too fast, for any interaction to occur. The isolation is total. It is permanent, and it is imposed not by any physical obstacle, but by the geometry of an expanding spacetime. This brings us to the central question we are circling. If the observable universe is 93 billion light-years across, if space itself is expanding, and if that expansion is accelerating, then what would it actually take to reach the edge? How long would the journey last? Is it even theoretically possible? To sharpen the question, let us put the journey in terms of everyday experience. If you got into a car today and drove at highway speed, roughly 100 kilometers per hour, heading straight for the edge of the observable universe, the trip would take approximately 500 trillion years. That is 5 followed by 26 zeros. The universe has existed for roughly 13.8 billion years, a number with 10 digits. The driving time has 27 digits. You would need to repeat the entire history of the universe, from the Big Bang to the present, roughly 36 million trillion times over, to match the driving duration. And this calculation does not account for the expansion of space, which would make the journey not merely longer, but infinite. Consider light speed instead. Light is the fastest thing in the universe. A beam of light could circle the entire Earth 7.5 times in a single second. At that extraordinary speed, it takes 8 minutes and 20 seconds to reach the Sunday, 4 years to reach the nearest star, 100,000 years to cross the Milky Way, 2.5 million years to reach the Andromeda galaxy, our nearest large galactic neighbor. These are immense timescales, but compared to the observable universe, they are trivial. Light would need 46.5 billion years to cross from us to the current edge of the observable universe if the universe were not expanding. But the universe is expanding, and that changes everything. We need to understand the different ways cosmologists measure distance, because this is where most confusion arises. There is the light travel distance, which is the distance light has actually traveled through space to reach us. There is the comoving distance, which is the distance measured in the current state of the universe, accounting for all the expansion that has occurred. And there is the proper distance, which is the distance measured at a single instant of cosmic time. These are not the same. The light travel distance to the CMB is about 13.8 billion light-years, because that is how long the light has been traveling. But the comoving distance to the CMB is about 46.5 billion light-years, because the matter that emitted the CMB has been carried that far away by expansion during the time the light was in transit. This distinction is fundamental. When we say the observable universe is 93 billion light-years across, we are using comoving distance. The actual light travel distance, the path that photons have followed through expanding space, is only about 13.8 billion light-years. But the starting points of those photons are now 46.5 billion light-years away. The universe has expanded behind the light as it travelled. This is not an error. It is the natural consequence of living in an expanding cosmos. The large-scale structure of the universe adds another layer of context. Galaxies are not scattered randomly. They are organized into an intricate web of filaments, walls, and voids. Galaxy clusters, containing hundreds or thousands of galaxies bound together by gravity, are connected by thin threads of matter called filaments, which stretch across hundreds of millions of light-years. Between the filaments are enormous voids, regions of nearly empty space that can span hundreds of millions of light-years across. The largest known structure, the Hercules Corona Borealis Great Wall, is estimated to be approximately 10 billion light-years across, making it the largest known structure in the observable universe. This cosmic web is not static, it is evolving. Gravity pulls matter along the filaments, feeding galaxy clusters with fresh material. Voids grow larger as matter drains away. And all of this, the entire structure, filaments, clusters, voids, and all, is embedded in the expanding fabric of space. On the largest scales, the web is being pulled apart. Clusters that are gravitationally bound will stay together, but the voids between them will grow, and the filaments will stretch and thin and eventually dissolve. The large-scale structure of the universe is temporary. Given enough time, expansion will erase it. There is a final piece of context that deserves mention before we move deeper. The observable universe, for all its enormity, is exquisitely smooth. The cosmic microwave background is uniform to 1 part in 100,000. The distribution of galaxies, on scales larger than about 1 billion light-years, is strikingly even. This smoothness is one of the great puzzles of cosmology. How did regions on opposite sides of the sky, regions that were never in causal contact, reach such similar conditions? The leading explanation is inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, which we will examine later. But the smoothness itself is a clue. It tells us that the observable universe, despite its vastness, is just a tiny patch of a much larger, perhaps infinitely larger, whole. The answer to our question involves some of the strangest physics ever discovered. It involves the bending of time, the stretching of space, the mysterious force of dark energy, and the ultimate fate of all things. And it begins with a simple, devastating realization that changes the character of the question entirely. The edge is not standing still, it is running away from us, and it is running faster than we can ever hope to follow. The central problem with reaching the edge of the observable universe is not a problem of engineering, it is not a problem of fuel, or speed, or willpower, or time. It is a problem woven into the very structure of spacetime. To understand it fully, we need to confront a concept that most people have heard of, but few truly grasp in its full weight. The expansion of the universe is accelerating, not merely continuing, accelerating, getting faster with every passing moment. In 1998, 2 independent teams of astronomers made a discovery that shocked the scientific world. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University, were studying a particular type of exploding star called a Type Ia supernova. These stellar explosions are extremely useful to astronomers because they all reach roughly the same peak brightness. When a white dwarf star, the dense remnant of a dead star, accumulates enough matter from a companion to exceed a critical mass of approximately 1.4 solar masses, it detonates in a thermonuclear explosion of remarkable consistency. Because these explosions are so uniform, they function as what scientists call standard candles. By comparing how bright a Type Ia supernova appears to be with how bright it actually is, astronomers can calculate its distance with remarkable precision. Both teams expected to find that the expansion of the universe was slowing down. This seemed like the obvious outcome. After all, gravity pulls matter together. The mutual gravitational attraction of all the matter in the universe should, logically, be acting as a brake on the expansion, gradually decelerating it over time. Think of a ball thrown upward. Gravity slows it down. Eventually, depending on how hard you threw it, it either slows to a stop and falls back, or escapes to infinity at an ever-decreasing speed. The only question seemed to be how quickly the deceleration was happening, and whether the universe would eventually stop expanding and begin to collapse back on itself, a scenario some cosmologists called the Big Crunch. What they found was the opposite. The distant supernovae were dimmer than expected, not by a tiny amount that could be explained away by dust or calibration errors, but by a significant, systematic margin. This meant the supernovae were further away than the standard cosmological models predicted. If the universe had been decelerating as expected, those supernovae should have been at a certain distance. Instead, they were further, meaning the universe had expanded more than expected over the intervening time. The only explanation was that the expansion was not slowing down, it was speeding up. This discovery was so startling, so counterintuitive, so at odds with the prevailing understanding of gravity and cosmology that both teams spent months checking and rechecking their data. They looked for systematic errors in their photometric measurements and in their calibration of the supernova brightness. They examined whether dust between us and the supernovae might be absorbing light and making them appear dimmer than they truly were. They tested whether the supernovae themselves might have been intrinsically dimmer in the early universe due to differences in the chemical composition of stars at earlier cosmic epochs. They scrutinized every assumption, every calibration, every piece of equipment. They found no error. The data was clear. The evidence was overwhelming. Something was pushing the universe apart, overcoming the pull of gravity on the largest scales. Something was causing the expansion to accelerate. That something was given the name dark energy. It is perhaps the most profound mystery in all of physics, and that is saying a great deal in a field that already contains quantum mechanics, black holes, and the origin of time. We do not know what dark energy is. We do not know why it exists. We cannot detect it directly with any instrument we possess. We can only infer its presence from its effects on the expansion of the universe, in the same way you might infer the existence of wind by watching leaves blow across a parking lot. The wind itself is invisible, but its effects are unmistakable. Current estimates suggest that dark energy accounts for approximately 68.3% of the total energy content of the universe. Ordinary matter, the atoms that make up stars, planets, rocks, water, and human beings, accounts for only about 4.9%. Dark matter, another mysterious substance that we can detect only through its gravitational effects on visible matter and on the bending of light, makes up roughly 26.8%. Take a moment to absorb that. The kind of matter we can see, touch, and study, the matter that makes up everything we have ever directly experienced, constitutes less than 5% of the total universe. The rest is dark, invisible, unknown. The universe is mostly made of things we do not understand. What exactly is dark energy? This remains one of the deepest open questions in physics. Several leading theories have been proposed, and each carries its own implications for the fate of the universe and, by extension, for our question about the journey to the edge. The simplest explanation is that dark energy is the cosmological constant, the very term that Einstein added to his equations and later called his greatest mistake. In this interpretation, dark energy is a property of empty space itself. Every cubic meter of space contains a fixed amount of energy, regardless of what else is in it. This vacuum energy is extraordinarily small by the standards of everyday physics, equivalent to roughly 6.9 times 10 to the negative 30 kilograms per cubic meter. That is a preposterously tiny number. But because the universe contains such an unfathomable volume of space, the total amount of dark energy is enormous, enough to dominate the dynamics of the entire cosmos. A second possibility is that dark energy is not constant but is instead a dynamic field that changes over time, sometimes called quintessence. In these models, the strength of dark energy could increase or decrease as the universe ages. If dark energy is getting stronger, the acceleration of expansion will increase, and the universe may eventually tear itself apart in a scenario called the Big Rip, in which the expansion becomes so violent that it overwhelms all forces, tearing apart galaxy clusters, then galaxies, then stars, then planets, then atoms. If dark energy is weakening, the acceleration might eventually cease, and the universe could return to decelerating expansion. Current observations are consistent with a cosmological constant, but they do not rule out quintessence entirely. The margin of uncertainty is still wide enough to leave room for surprises. A third and more exotic possibility is that dark energy is a sign that our understanding of gravity itself is incomplete. Perhaps general relativity, which has passed every test we have devised for it in our local cosmic neighborhood, behaves differently at the largest scales. Perhaps the equations need modification when applied to the entire observable universe. This is the domain of modified gravity theories, which attempt to explain the acceleration without invoking a new form of energy. While these theories are mathematically possible, they have struggled to match the full range of cosmological observations as well as the cosmological constant does. Regardless of which explanation is correct, the observable consequences are the same for our purposes. The expansion of the universe is accelerating. The acceleration has been measured independently by multiple methods, including supernova distances, baryon acoustic oscillations, the growth rate of cosmic structure, and gravitational lensing of the cosmic microwave background. All methods agree the acceleration is real, and it means that reaching the edge of the observable universe is not merely difficult, it is physically impossible. Dark energy behaves in a way that is deeply counterintuitive. Unlike ordinary matter and radiation, which become diluted as space expands, dark energy maintains a roughly constant density per unit volume. This means that as space expands, a new volume is created, more dark energy appears to fill it. The total amount of dark energy in the universe increases as the universe grows. This is what gives dark energy its remarkable power. The more space expands, the more dark energy there is. The more dark energy there is, the faster space expands. It is a positive feedback loop, a runaway process, and it has been the dominant force shaping the universe for approximately the last 5 billion years. Before dark energy took over, the expansion was indeed slowing down, just as the ball thrown upward analogy would suggest. In the first few billion years after the Big Bang, the universe was dense enough that gravity's braking effect was significant. The expansion decelerated. But as the universe grew and matter became more diluted, gravity's influence weakened. Meanwhile, dark energy, which does not dilute, maintained its strength. Eventually, dark energy's repulsive effect overtook gravity's attractive effect, and the expansion began to accelerate. That transition happened roughly 5 billion years ago, around the time our sun and solar system were forming. We were born into a universe that was already running away. But here's the problem. If the expansion is accelerating, then distant objects are receding from us at ever-increasing speeds. And beyond a certain distance, they are receding faster than the speed of light. This statement tends to provoke objections. Does this not violate Einstein's special relativity? Does special relativity not state that nothing can travel faster than light? The answer is subtle and crucial. Special relativity states that nothing can travel through space faster than light, but the expansion of space is not motion through space. It is the growth of space itself. Objects carried along by the expansion are not moving through a fixed background. The background itself is stretching, carrying objects along with it like raisins in a rising loaf of bread. Each raisin is stationary within the dough, but as the dough expands, the distance between raisins increases. Raisins that are far apart separate faster than raisins that are close together, simply because there is more dough between them to expand. At sufficient separation, the rate of separation can exceed any speed, including the speed of light. No raisin is moving through the dough at all. The dough is doing all the work. This is not a loophole or a technicality. It is a fundamental feature of general relativity. Einstein's equations explicitly allow the expansion of space to proceed at any rate. There is no speed limit on how fast space can grow. The speed of light limit applies to objects moving through space, not to the growth of space itself. The two are completely different phenomena governed by different aspects of the theory. This creates what cosmologists call the Hubble sphere, sometimes called the Hubble radius or Hubble horizon. The Hubble sphere is the distance at which the recession velocity due to expansion equals the speed of light. For the current expansion rate of approximately 67.4 kilometers per second per megaparsec, the Hubble radius works out to roughly 14.4 billion light-years. Objects at this distance are currently receding from us at exactly the speed of light. Objects beyond this distance are receding faster than light. Light emitted by those objects today is swimming upstream against an expanding river of space, and at the Hubble radius, the river flows exactly as fast as the light can swim. Beyond that point, the river wins. The light moves backward, carried away by expansion faster than it can advance toward us. Now, one might assume that the Hubble sphere defines the edge of what we can see. It does not. This is one of the most common misconceptions in cosmology. The observable universe extends much further than the Hubble sphere because the expansion rate has changed over cosmic history. In the early universe, the expansion rate was much higher. Then it slowed as gravity acted on the dense matter. Then it began accelerating again as dark energy took over. Light that was emitted from well beyond the current Hubble radius, long ago when conditions were different, managed to reach us because the expansion rate was not always what it is today. Some of that light was initially carried away from us by expansion, but as the expansion rate changed, it was eventually able to make progress toward us and ultimately arrive. But light emitted today from beyond the Hubble sphere will never reach us. Not in a million years, not in a trillion, not ever. It is permanently lost. The current Hubble sphere is, for all future photons, a one-way door. Light can leave our neighborhood and enter the space beyond it, but light from beyond it can no longer enter ours. And it gets worse. The acceleration of expansion means the Hubble sphere is not growing fast enough to keep up with the recession of distant objects. In a universe dominated by dark energy, the Hubble sphere approaches a fixed limit. This fixed limit is called the cosmological event horizon. The event horizon is the ultimate boundary. It defines the maximum distance from which a signal emitted today could ever, in principle, reach us, even given an infinite amount of time. Any light, any signal, any gravitational wave, any particle emitted today from beyond the event horizon will never reach us. Period. No waiting will change that. No patience will be rewarded. The event horizon is currently at a co-moving distance of approximately 16.7 billion light-years. Everything beyond that distance is, from this moment forward, permanently and irrevocably out of reach. Not temporarily, not with better technology, not with faster ships, permanently. The word permanently deserves emphasis because it is so rarely used accurately. Most things that seem permanent are not. Mountains erode, stars die, galaxies collide and merge. But the event horizon is truly permanent, as long as dark energy continues to dominate the expansion, and there is no evidence whatsoever that dark energy will stop. The event horizon is not a physical barrier. There is no wall, no edge, no boundary marker, no detectable feature at that distance. An astronaut crossing it would notice nothing unusual. The laws of physics at the event horizon are exactly the same as anywhere else. It is a purely informational boundary, a limit on causal connection. It separates regions of spacetime that can influence each other from regions that cannot. And as the expansion accelerates, more and more objects are crossing this boundary, passing beyond our ability to communicate with them, vanishing from our accessible universe like ships sailing over the horizon of a cosmic ocean that stretches in every direction. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most precise measurements ever made of the cosmic microwave background and the cosmological parameters that describe the universe. Its data confirmed the accelerating expansion with extraordinary precision. The data also confirmed the age of the universe at 13.799 billion years plus or minus 21 million years. It confirmed the composition of the universe as roughly 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary matter. It measured the Hubble constant with unprecedented accuracy, and every single measurement pointed to the same conclusion. The universe is expanding, the expansion is accelerating, and the acceleration shows no sign of relenting. There is, however, an unresolved tension in our measurements that deserves mention. The Hubble constant, as measured by the Planck satellite from the cosmic microwave background, gives a value of approximately 67.4 kilometers per second per megaparsec. But when astronomers measure the Hubble constant using nearby supernova distances and Cepheid variables, a method championed by Adam Riess and the show's team, they get a higher value, approximately 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has persisted for over a decade and shows no sign of going away. It may be a systematic error in one or both methods. Or it may be a sign that our cosmological model is incomplete, that something about dark energy or the expansion history is more complex than the simple cosmological constant allows. If the higher value is correct, the implications for our journey become even more stark. A faster expansion rate means the Hubble sphere is closer, the event horizon is nearer, and the fraction of the observable universe that is accessible shrinks further. If the lower value is correct, the situation is still hopeless, merely slightly less so. Either way, the conclusion is the same. The edge of the observable universe is unreachable by any physically possible means. There is another way to appreciate the impossibility of this journey. Consider the total energy required. To accelerate even a single kilogram of matter to the speed of light would require an infinite amount of energy. This is a direct consequence of special relativity. As an object approaches the speed of light, its relativistic mass increases without bound, and the energy required to accelerate it further grows correspondingly. At 90% of the speed of light, the energy required to push 1 kilogram to that speed is approximately 3.6 times 10 to the 16th joules, equivalent to the energy released by several large nuclear bombs. At 99%, the energy is roughly 3 times higher. At 99.9%, higher still, and at 100%, the energy is infinite. No engine, no power source, no amount of fuel could reach it. So even setting aside the expansion of space, even in a hypothetical non-expanding universe, traveling at the speed of light is impossible for any object with mass. The best we could do, in principle, is approach the speed of light asymptotically, getting ever closer but never quite reaching it. And as we have seen, even at the speed of light, the journey would be impossible because of expansion. Reaching 99.999% of the speed of light would not help. The expansion is superluminal at the edge. You would need to exceed the speed of light, which you cannot. The laws of physics are unanimous on this point. There is no way. What does all of this mean for our hypothetical journey to the edge of the observable universe? It means the destination is not fixed. The edge of the observable universe is defined by the cosmic microwave background, the most distant light we can detect. That light was emitted 13.8 billion years ago from matter that was, at that time, only about 42 million light-years from our current location. But since then, expansion has carried that matter to a co-moving distance of approximately 46.5 billion light-years, and every moment, every second, the expansion carries it further still. If you began traveling toward the edge of the observable universe at the speed of light, starting today, you would never reach it. This is the core of the problem, the heart of the impossibility, and it is worth stating with absolute clarity, you would never reach it, not ever. The space between you and the edge would expand faster than you could cross it. You would be like a swimmer trying to reach the far side of a pool that is stretching faster than you can swim. No matter how hard you swim, no matter how fast you move through the water, the far wall recedes. Your muscles burn, your arms pull, you move forward through the water, but the wall moves backward faster. After billions of years of travel at light speed, you would not be closer to the edge. You would actually be further from it than when you started. Let us trace this journey in more detail, because the mechanics are worth understanding. Suppose you launch from Earth at the speed of light, heading toward a point on the cosmic microwave background that is currently 46.5 billion light-years away. In your first year of travel, you cover 1 light-year of distance through local space. But during that same year, the expansion of space has pushed the edge roughly 3.3 light-years further away. You have made 1 light-year of progress, but lost 3.3 light-years to expansion. After 1 year, the edge is now further from you than when you started by roughly 2.3 light-years. And the rate of this loss is not constant. It is accelerating. In your second year, the expansion will push the edge even further. In your 10th year, further still. The deficit grows without bound. After 1 billion years of light-speed travel, you would have crossed roughly 1 billion light-years of local space. But the cumulative expansion during that time would have pushed the edge tens of billions of light-years further away. The gap between you and the destination would be larger than the original distance. And the universe itself would be vastly larger. The Hubble constant would still be roughly the same. But the distances would have grown, and the recession velocities at those distances would be correspondingly higher. You would be chasing a target that is not merely running away, but accelerating away. Now consider what you would observe during this journey. In the first few billion years, you would see the galaxies ahead of you slowly redshifting, their light stretching as the space between you and them continues to grow. Galaxies behind you, back toward Earth, would also be receding, their light redshifting as well. Over time, the light from more and more of these galaxies would redshift below detection limits. The sky would darken, the number of visible objects would decline. After tens of billions of years of travel, you would find yourself in an increasingly empty cosmos. The galaxies that were once ahead of you, your waypoints and landmarks, would have been carried beyond your event horizon. You would be alone in an expanding void, surrounded by darkness, heading toward a destination that does not, in any operational sense, exist. This is not a matter of needing a faster ship. There is no ship, real or hypothetical, that can outrun the expansion. The speed of light is the absolute maximum velocity for any object, signal, or influence moving through space, and the expansion of space is not motion through space. You cannot compete with it by going faster, because speed and expansion are fundamentally different phenomena. It is like trying to outswim a river by swimming faster. You can swim faster than the current, and you will make progress. But if the river accelerates, and keeps accelerating, eventually the current outruns you, no matter how fast you swim. The expansion of the universe is an ever-accelerating river, and we are swimmers who have already been outpaced. This is not science fiction. This is the straightforward, unavoidable, mathematically certain consequence of the measured expansion rate and its acceleration. It is built into the equations of general relativity. It has been confirmed by every major cosmological observation of the past quarter century, from the supernova measurements of 1998 to the Planck satellite data of 2013 to the ongoing baryon acoustic oscillation surveys and gravitational lensing studies. There is no controversy about this. There is no alternative interpretation. The edge of the observable universe is, and will forever remain, beyond the reach of any traveler moving at any physically possible speed. Let us make this concrete with specific numbers. Right now, the most distant galaxies we can observe, those faint smudges in the Hubble and James Webb deep fields, are receding from us at roughly 3 times the speed of light. Their recession velocity, driven entirely by the expansion of space, is approximately 900,000 kilometers per second. A spacecraft traveling at the speed of light would be moving at only 1/3 that rate. The gap would widen by roughly 600,000 kilometers every second. After 1 year of light-speed travel towards such a galaxy, you would be approximately 19 trillion kilometers further from it than when you started. After 1 billion years, you would be millions of light-years further away. The faster you chase, the faster it runs. Even if we consider objects much closer than the edge, the problem persists at sufficient distances. A galaxy currently 10 billion light-years away is receding at approximately 2.3 times the speed of light, unreachable. A galaxy at 5 billion light-years is receding at roughly 1.15 times the speed of light, still unreachable in the long term, because the acceleration will eventually push it past the event horizon. The accessible universe, the portion we could even theoretically reach, is a shrinking subset of what we can see. There is a concept in cosmology called the particle horizon. It is the maximum distance from which particles could have traveled to reach us since the beginning of the universe. It represents the boundary of the observable universe, currently at a come-moving distance of approximately 46.5 billion light-years. Then there is the event horizon, the forward-looking boundary, at approximately 16.7 billion light-years, defining the maximum distance from which signals sent today could ever reach us. And there is the Hubble radius, at roughly 14.4 billion light-years, where the recession speed equals the speed of light. These 3 horizons define our cosmic situation. The particle horizon is our past light cone, the event horizon is our future light cone. The Hubble radius is the present boundary of superluminal recession. Together, They paint a picture of a universe that is simultaneously revealing its past and hiding its future. We can see far more than we can ever reach. We can observe galaxies that are already lost to us, whose light departed long ago from regions that are now irrecoverably beyond the event horizon. We are watching ghosts. The galaxies whose light we see in the deep field images are already gone from our accessible universe. They crossed the event horizon millions or billions of years ago. Their light is all that remains, a final postcard from a place we will never visit, sent from an address that no longer exists. Let us put concrete numbers on this loss. In the Hubble ultra-deep field, the most distant galaxies we can see have a redshift of approximately 11, meaning their light has been stretched by a factor of 12 during its journey. The matter that emitted that light is now approximately 32 billion light-years away. Since the event horizon is at roughly 16.7 billion light-years, this matter is already twice as far away as anything we could ever reach. We are looking at objects that have been permanently disconnected from us for billions of years. The image is an archaeological record, not a live feed. Those galaxies have evolved, changed, perhaps merged with other galaxies, perhaps collapsed, perhaps spawned civilizations that rose and fell, and we will never know any of it. The photons we captured are the last information we will ever receive from those regions. The James Webb Space Telescope has pushed even further. Some of its earliest observations revealed galaxies at redshifts of 13 and beyond, corresponding to objects that are now more than 33 billion light-years away. These objects are so far beyond the event horizon that they might as well be in a different universe. In a very real sense, they are. They will never influence our future. We will never influence theirs. The gap is absolute. Now consider the rate at which objects are being lost. Calculations based on the lambda CDM model, the standard model of cosmology, show that the comoving volume of the accessible universe, the region from which signals can still reach us in the future, is shrinking with every passing moment. The number of galaxies within our event horizon is declining. Some estimates suggest that roughly 97% of the galaxies currently visible in the observable universe are already beyond the event horizon. Only about 3% of the galaxies we can see are still within our potential reach, and that 3% is shrinking. Over the coming billions of years, more galaxies will be carried past the event horizon. Their light will redshift, fade, and eventually become undetectable. The observable universe, in a practical sense, will shrink, not because the particle horizon is contracting, but because the objects within it are fading from view. The distinction matters. The particle horizon will continue to grow, slowly, as light from earlier epochs continues to reach us from the most extreme distances. But the useful observable universe, the part from which we receive detectable signals from recognizable objects, will contract. In the far future, perhaps 100 billion years from now, the only galaxies visible from the merged remnant of the Milky Way and Andromeda will be the handful of local group members that remain gravitationally bound. Everything else will have faded into the background radiation, their photons stretched to wavelengths longer than the observable universe itself. The cosmic microwave background will have redshifted to temperatures below 10 to the negative 30 degrees Kelvin, far below any conceivable detection threshold. A civilization arising in that era would have no observational evidence that the universe was ever any different. They would see one galaxy in an infinite void. Their cosmology would be fundamentally, tragically wrong. Not because they failed to look, but because the universe would have erased its own history. Something is deeply wrong with our intuitive picture of the universe. We imagine space as a stage, fixed and immutable, on which objects move. We imagine that if we can see something, we can, in principle, reach it. We imagine that distances are obstacles to be overcome, not barriers to be accepted. But space is not a stage. It is a living, growing, dynamic entity, and it is growing faster than anything in it can move. The distances we measure today are not the distances that will exist tomorrow. And the further we look, the faster those distances grow. The universe is not merely big, it is getting bigger, and the rate at which it is getting bigger is itself getting bigger. This cascading growth is the defining feature of our cosmic era, and it places an absolute, inviolable limit on how much of the cosmos, any civilization, anywhere, at any level of technological advancement, will ever be able to explore. Consider what this means from the perspective of the universe itself, if such a perspective could exist. The cosmos contains unimaginable richness. Trillions of galaxies, each unique, each containing hundreds of billions of star systems, many of them hosting planets, some of those planets perhaps harboring life. And all of this richness is being systematically isolated. Each pocket of gravitationally bound matter is being walled off from every other pocket by the relentless growth of space. The universe is not just expanding, it is fragmenting. It is breaking itself into disconnected pieces that will never interact again. Every galaxy cluster is becoming its own universe, sealed away from everything else by an ever-widening gulf of expanding space. The mathematics of this situation was worked out in careful detail by several cosmologists over the past 2 decades. The key papers include the influential work by Tamara Davis and Charles Lineweaver from 2004, who wrote a paper titled Expanding Confusion: Common Misconceptions of Cosmological Horizons and the Superluminal Expansion of the Universe. In that paper, they demonstrated that many widely held intuitions about the expanding universe are simply wrong. Objects we can currently see are already receding faster than light. The Hubble sphere is not the same as the observable universe, and the expansion of space does not violate special relativity. Their paper is a masterclass in careful thinking about counterintuitive physics, and it remains one of the most cited papers in modern cosmology. Let us pause here and absorb the full weight of what we have discussed. The observable universe is 93 billion light-years across, a sphere of light containing 2 trillion galaxies and 700 sextillion stars. That sphere, stretching tens of billions of light-years in every direction, is all we will ever know. The universe is 13.8 billion years old. Light is the fastest thing in existence, the cosmic speed limit, the ultimate boundary of causality. And even light, travelling since the first moments of creation, has only been able to illuminate a fraction of what exists. The rest is dark, silent, and forever beyond our reach. We live in a lit room in an infinite mansion, and the doors are locked. The cosmos we can observe, spanning those vast billions of light-years, is a window into reality, but it is a window that is slowly going dark. The cosmic background radiation continues to fade. The distant galaxies continue to recede, and the expansion continues to accelerate, indifferent to our desire to understand what lies beyond. But here's what makes this truly terrifying. The accessible universe, the portion we could theoretically reach or communicate with, is not merely small, it is shrinking. Every second, galaxies that were once within our cosmic reach are crossing the event horizon and becoming permanently isolated from us. The rate of this loss is accelerating. The number of galaxies we will ever be able to interact with is declining, and it will continue to decline until, in the far future, our cosmic neighborhood will consist of only the gravitationally bound, local group of galaxies, the Milky Way, Andromeda, a few dozen smaller companions, drifting together through an otherwise empty void, a tiny island of matter in a universe that has, from their perspective, erased everything else. Think about what that means for the question of life elsewhere in the cosmos. If there are other civilizations out there, in distant galaxies, looking up at their own skies and asking the same questions we ask, they too are trapped within their own event horizons. They too are watching their accessible universe shrink. They too are losing galaxies to expansion, watching the lights go out one by one, and they have no way to reach us, just as we have no way to reach them. 2 civilizations could exist simultaneously, both capable of interstellar travel, both looking for companionship in the cosmos, and still be forever separated by the expansion of space. The universe may be full of life, and that life may be utterly, permanently alone, each civilization an island, each island surrounded by an ever-widening ocean of expanding space. Each one unaware of the others, not because they are rare, but because the cosmos is structured to keep them apart. This is the architecture of isolation. It is not an accident. It is not a quirk. It is built into the laws of physics, into the geometry of spacetime, into the nature of dark energy and the expansion of the cosmos. The universe does not merely contain loneliness, it manufactures it. At the largest scales, the cosmos is a machine for creating distance, for separating matter, for ensuring that no two sufficiently distant objects will ever interact again. And we are part of that machine, carried along by the same expansion that isolates us, participants in a process that we can understand but cannot resist. Given the enormity of the challenge, let us now explore what it would actually take to attempt a journey to the edge of the observable universe. We will consider 5 different approaches, each representing a different level of technological ambition and physical possibility. For each, we will examine what it offers, what it would involve, and where it ultimately fails. This is the longest part of our journey, because the details matter. Each approach illuminates a different facet of the problem, and together they form a complete picture of just how deeply the universe has constrained our reach. The first approach is the one closest to our current technology: conventional propulsion, chemical rockets, ion drives, solar sails. The tools we actually possess, right now, in the early decades of the 21st century, consider our fastest spacecraft. The Parker Solar Probe, launched by NASA in 2018, is the fastest human-made object ever constructed. During its close passes around the Sun, using the Sun's gravity to accelerate it to extraordinary speeds, the Parker Solar Probe has reached velocities of approximately 635,000 km per hour. That is roughly 176 km per second. To put that in perspective, it could fly from New York to Los Angeles in about 23 seconds. It is a triumph of engineering, and it is absurdly, heartbreakingly slow compared to the distances we are discussing. At the speed of the Parker Solar Probe, how long would it take to reach the edge of the observable universe? The edge is approximately 46.5 billion light-years away. A light-year is roughly 9.46 trillion kilometers. The total distance is therefore approximately 4.4 times 10 to the 26th power kilometers. At 176 kilometers per second, the travel time works out to approximately 79 trillion years. To write that out, 79 followed by 12 zeros. For context, the universe itself is only 13.8 billion years old. This journey would take roughly 5,700 times longer than the current age of the universe. And remember, this calculation ignores the expansion of space entirely. It treats the distance as fixed, which it is not. With expansion factored in, the journey becomes not merely long but infinite. The destination moves away faster than the probe approaches. The Parker Solar Probe would never arrive, not even close. But the Parker Solar Probe is not representative of a sustained interstellar mission. Its peak speed occurs only during brief close encounters with the Sunday. For a more realistic benchmark, consider Voyager 1, launched in 1977 and currently the most distant human-made object from Earth. Voyager 1 is traveling at roughly 17 kilometers per second, or about 61,000 kilometers per hour. It has been traveling for nearly 5 decades and is currently about 24 billion kilometers from Earth, or roughly 164 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. Voyager 1 has not even left the solar system's wider gravitational influence. The Oort cloud, the outermost shell of icy bodies orbiting the Sun, extends to perhaps 100,000 astronomical units. At Voyager's current speed, it would take roughly 30,000 years to cross the Oort cloud, 30,000 years, just to leave our solar system's extended neighborhood. At Voyager's speed, reaching the nearest star, Proxima Centauri at 4.24 light-years, would take approximately 75,000 years. Reaching the center of our galaxy, roughly 26,000 light-years away, would take roughly 460 million years. And reaching the edge of the observable universe, 46.5 billion light-years away, would take approximately 823 quadrillion years, or roughly 60 billion times the current age of the cosmos. The numbers are striking. They are so large that they become meaningless. Our fastest technology would take billions of times the age of the universe to cover a distance that light itself cannot cross. Conventional propulsion is not merely inadequate, it is irrelevant. To appreciate just how irrelevant, consider this scaled comparison. If you shrank the distance from Earth to Proxima Centauri down to 1 meter, the distance to the edge of the observable universe would be approximately 11 billion meters, or roughly 11 million kilometers. That is about 29 times the distance from the Earth to the Moon. So even if we could master interstellar travel, even if we could cross the gap to the nearest star routinely, we would have covered the equivalent of 1 meter out of a journey that stretches 29 times further than the Moon. And this comparison still does not account for expansion, which would make the effective journey infinite. If instead we scale down the Milky Way to something we can hold in our hands, say the size of a dinner plate 30 centimeters across, then the observable universe would be a sphere roughly 140 kilometers in radius, a dinner plate galaxy floating in a bubble the size of a small country. And within that bubble, 2 trillion other dinner plates, each containing hundreds of billions of stars, each separated from its neighbors by meters or tens of meters of empty space. Reaching the edge of this model from the center would be like walking from a city center to a suburb. But in the real universe, that walk takes infinite time. The model breaks. The metaphor fails. 1355. There is no earthly experience that maps cleanly onto the problem. The second approach involves traveling at a significant fraction of the speed of light. This is the realm of speculative but physically plausible technology. Concepts that do not violate any known law of physics but are far beyond our current engineering capabilities. Several propulsion concepts have been proposed over the decades that could, in principle, achieve relativistic speeds. Nuclear pulse propulsion was one of the first serious proposals. Project Orion, conceived in the late 1950s and early 1960s by scientists including Ted Taylor and Freeman Dyson, envisioned a spacecraft propelled by detonating nuclear bombs behind a massive pusher plate. The explosions would accelerate the ship in a series of controlled bursts. Each bomb would produce a pulse of plasma that would strike the pusher plate, imparting momentum to the ship. The original designs envisioned ships the size of ocean liners, carrying thousands of nuclear charges, accelerating to several percent of the speed of light over a period of years. Calculations suggested that a large Orion-type vessel could reach 3 to 5% of the speed of light, making it feasible for interstellar travel to the nearest stars within a few human generations. The project was ultimately abandoned, partly because of the 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in space, and partly because of the sheer scale and audacity of the concept. But the physics was sound. No known law of nature prevents nuclear pulse propulsion from working. It is simply too dangerous, too politically unacceptable, and too enormous for any nation or organization to attempt. At 5% of the speed of light, the fastest speed Project Orion could achieve, the travel time to the edge of the observable universe would still be approximately 930 billion years without expansion, and infinite with expansion. Even this heroic propulsion system, which would consume thousands of nuclear warheads, would not come within a factor of 100 of reaching the nearest galaxy cluster, let alone the edge of the observable cosmos. Laser sail propulsion represents a more recent approach. The Breakthrough Starshot Initiative, announced in 2016 by venture capitalist Yuri Milner and physicist Stephen Hawking, proposes using a ground-based laser array to accelerate tiny, lightweight probes to roughly 20% of the speed of light. These probes, each weighing only a few grams with ultra-thin reflective sails measuring roughly 4 meters across, would ride the momentum of the laser light like a sailboat rides the wind. At 20% of light speed, a probe could reach Proxima Centauri in about 20 years. The concept is technically challenging, but not physically impossible. The main obstacles are engineering problems, like building a sufficiently powerful laser array with roughly 100 gigawatts of output, protecting the probes from interstellar dust impacts at relativistic speeds, and decelerating the probes upon arrival, since the laser can only push, not pull. But even at 20% of the speed of light, the journey to the edge of the observable universe would take approximately 233 billion years without expansion, roughly 17 times the current age of the universe, and once again, infinite with expansion. Laser sails are a promising technology for reaching nearby stars. They are utterly irrelevant for reaching the edge of the cosmos. Fusion drives, antimatter engines, and Bussard ramjets have also been proposed, each with varying degrees of theoretical plausibility. A fusion drive, using the energy released by fusing hydrogen into helium, the same process that powers the Sun, could potentially achieve exhaust velocities of several percent of the speed of light. The British Interplanetary Society's Project Daedalus, designed in the 1970s, proposed a fusion-powered probe that could reach Barnard's star, roughly 6 light-years away, in about 50 years, achieving a maximum speed of roughly 12% of the speed of light. An antimatter drive would be even more powerful. When matter meets antimatter, the two annihilate completely, converting all of their mass into energy. This is the most efficient energy conversion process known to physics, 100% efficient compared to nuclear fission's roughly 0.1% and fusion's roughly 0.7%. In theory, an antimatter drive could achieve speeds approaching a significant fraction of the speed of light. In practice, we can produce only nanograms of antimatter at a cost of trillions of dollars per gram, and we have no way to store it safely in the quantities needed for propulsion. A Bussard ramjet, proposed by physicist Robert Bussard in 1960, would scoop up interstellar hydrogen as fuel, allowing it to accelerate continuously without carrying all its fuel from the start. A massive electromagnetic funnel, perhaps hundreds of kilometers across, would sweep up the thin hydrogen gas that permeates interstellar space, feeding it into a fusion reactor. In theory, such a craft could accelerate indefinitely, reaching very high fractions of the speed of light. In practice, detailed analyses have shown that the interstellar medium is too thin and the drag from the magnetic scoop too high for the concept to work as originally envisioned. The scoop would create more drag than the fusion reactor could overcome. Rather than accelerating, the ramjet would actually decelerate. It is a beautiful idea that fails on the details. Let us be generous. Let us assume a spacecraft capable of traveling at 90% of the speed of light. This is far beyond anything we can currently build, but it does not violate physics. At this speed, special relativity introduces a phenomenon called time dilation. As an object approaches the speed of light, time for that object slows down relative to a stationary observer. The factor by which time slows is called the Lorentz factor, and at 90% of the speed of light, it equals approximately 2.29. This means that for every 2.29 years that pass on Earth, only 1 year passes on the spacecraft. The travelers age more slowly than the people they left behind. Without accounting for the expansion of space, the naive travel time to the edge of the observable universe, 46.5 billion light-years, at 90% of the speed of light, would be approximately 51.7 billion years in the Earth frame. In the traveler's frame, time dilation would compress this to roughly 22.6 billion years. Both numbers are longer than the age of the universe. The travelers would need to survive for roughly 1.5 times the current age of the cosmos, even with time dilation helping them. But this calculation is misleading because it ignores expansion. With expansion factored in, the journey does not merely take longer, it becomes impossible. The space ahead of the traveler expands faster than the traveler crosses it. At 90% of the speed of light, the traveler makes progress through local space at a respectable rate, but the recession velocity of the edge is several times the speed of light. The traveler is, in net terms, falling behind. Every year of travel puts the destination further away, not closer. At 99% of the speed of light, the Lorentz factor rises to about 7.09. Time dilation becomes more dramatic. The journey is compressed further in the traveler's frame. But the same fundamental problem remains. The destination is expanding away at superluminal speeds. No matter how close to the speed of light you travel, you cannot outrun the expansion. The universe does not care how fast you go. It simply expands faster, There is a subtlety worth exploring. At very high speeds, a traveler experiences extreme time dilation. In principle, an astronaut accelerating at 1 g, the comfortable pull of Earth's gravity, could traverse enormous distances within their own lifetime. After roughly 1 year of constant 1 g acceleration, the spacecraft would reach about 77% of the speed of light. After 5 years, about 99.9%. After 10 years, the craft would be moving at 99.99% of the speed of light, and the Lorentz factor would be enormous, meaning the traveler would experience time passing extremely slowly relative to the rest of the universe. Let us work through a concrete example to feel the power and the ultimate futility of this approach. Imagine a spacecraft that launches from Earth and accelerates at 1 g continuously. After 1 year of the traveler's time, the ship is moving at roughly 77% of the speed of light and has covered about half a light year. On Earth, about 1.2 years have passed. After 10 years of the traveler's time, the ship has covered roughly 4,900 light years, and roughly 5,000 years have passed on Earth. The Lorentz factor is enormous. The traveler is aging slowly while the universe ages rapidly around them. After 20 years of the traveler's ship time, the craft has covered roughly 300 million light years, and hundreds of millions of years have passed on Earth. This is already deep into intergalactic space. The traveler has crossed a significant fraction of the distance to the Coma cluster, one of the nearest large galaxy clusters, but the edge of the observable universe is still tens of billions of light years away. After 40 years of ship time, something approaching a human working lifetime, the traveler has covered an enormous distance in the Earth frame, potentially billions of light years. But the universe has aged by trillions of years. Earth's sun has long since exhausted its fuel, expanded into a red giant, and collapsed into a white dwarf. Human civilization, if it survived, has had to move to other star systems, other galaxies, and still, the traveler is nowhere near the edge. The expansion has pushed it further away during the journey. The gap between the traveler and the edge has grown, not shrunk. In the traveler's reference frame, enormous distances could be crossed in what feels like a few decades. A traveler accelerating at 1 g for 28 years of ship time could, in principle, cross the entire observable universe as it exists today, if the universe were not expanding. During those 28 years of the traveler's life, trillions of years would pass on Earth. The time dilation would be that extreme, but the universe is expanding, and this is where even the most extreme time dilation fails. Even if the traveler experiences only decades of personal time, the objective distance to the edge is growing faster than the traveler approaches it. The time dilation helps the traveler survive the journey, but it does not change the physics of expansion. The edge recedes superluminally. The traveler's velocity through space is subluminal. The gap grows. And the cosmological event horizon, at 16.7 billion light-years, represents an absolute limit. No amount of acceleration, no degree of time dilation, no length of journey can take the traveler past the event horizon. Beyond it, destinations recede faster than the traveler approaches, and this remains true regardless of the traveler's velocity or acceleration profile. The edge of the observable universe is nearly 3 times further than the event horizon. It is not merely unreachable. It is unreachable by a margin so large that it mocks the very concept of reaching. The third approach ventures into the realm of theoretical physics. What about faster than light travel? What about warping the fabric of spacetime itself? In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a remarkable paper. Alcubierre proposed a solution to Einstein's field equations of general relativity that described a bubble of warped spacetime. Inside the bubble, a spacecraft would be perfectly at rest relative to local space. It would feel no acceleration. No force would act on its occupants. But the bubble itself, this pocket of flat spacetime, could move through the larger spacetime at any speed, including speeds far greater than light. The trick was that the spacecraft was not moving through space. Space itself was being contracted in front of the bubble and expanded behind it. The spacecraft was surfing a wave of spacetime, like a surfer riding a wave across the ocean. The surfer is not swimming. The wave is doing the moving. This became known as the Alcubierre warp drive, and it captured the imagination of physicists and science fiction writers alike. On paper, it is consistent with general relativity. It does not violate the speed of light because nothing inside the bubble is moving through space faster than light. The space itself is doing the moving, and there is no speed limit on how fast space can expand or contract. In principle, a warp bubble could carry a spacecraft to the edge of the observable universe faster than light could travel through normal space. It could potentially outrun the expansion itself. But here's the problem, and it is a deep one. The Alcubierre drive requires exotic matter. Specifically, it requires matter, or energy, with a negative energy density. In everyday physics, energy is always positive, mass is always positive, gravity always attracts. But the warp drive needs regions of spacetime where the energy is negative, which would create a repulsive gravitational effect, allowing space to be contracted and expanded in the required pattern. Without this exotic matter, the warp bubble cannot form. Negative energy is not entirely fictional. There are quantum phenomena that produce small regions of negative energy density. The Casimir effect, discovered by the Dutch physicist Hendrik Casimir in 1948, predicts and produces a tiny attractive force between two closely spaced conducting plates in a vacuum, arising from the suppression of certain quantum fluctuations between the plates. This effectively creates a region of negative energy density between them, but the amount of negative energy involved is minuscule, far too small to power a warp drive. Early calculations by Alcubierre and others suggested that the total energy required for a warp bubble would be equivalent to the mass energy of the entire observable universe, roughly 10 to the 60th joules. This is a staggering number. Later refinements reduced this somewhat. Chris van den Broek showed in 1999 that by modifying the geometry of the bubble, the energy requirements could be reduced considerably. Harold White at NASA's EagleWorks laboratory proposed further refinements in the 2010s that reduced the requirements to something closer to the mass energy of a planet, still enormous but less absurd than the mass energy of the universe. However, even these optimistic estimates remain far beyond any conceivable technology, and many physicists question whether the required configurations of negative energy are physically realizable at all. Furthermore, even if a warp drive could somehow be constructed, it would face the same expansion problem at the largest scales. The expansion of space at the edge of the observable universe exceeds the speed of light by a factor of 3 or more. A warp bubble would need to exceed this rate to make progress. Whether a warp bubble could achieve superluminal speeds relative to an already superluminally expanding background is an open question. Some physicists argue that the bubble's velocity is measured relative to the local spacetime, which itself is being carried by expansion. In this view, a warp drive moving at 10 times the speed of light through local space might still fall behind if the background expansion rate is even higher. There are also fundamental concerns about causality. In many formulations of general relativity, faster-than-light travel creates the possibility of closed time-like curves, paths through spacetime that loop back on themselves, allowing an object or signal to return to its own past. This would enable sending messages backward in time, which creates paradoxes that most physicists regard as unphysical. If you can send a message faster than light, then by combining different reference frames, you can construct a scenario in which the message arrives before it was sent. This violates causality, the principle that causes must precede their effects, which is generally regarded as one of the most fundamental requirements of any self-consistent physical theory. The math is striking. Even the most optimistic theoretical framework for superluminal travel is hedged by energy requirements that dwarf the output of every star in every galaxy, by stability problems that may be unsolvable, by causality paradoxes that threaten the logical structure of physics itself, and by deep questions about whether the required forms of exotic matter can exist in the quantities needed. The warp drive is a beautiful mathematical curiosity. It is not, by any current understanding, a viable technology. And even if it were, the expansion of space at the scale of the observable universe would remain a formidable, perhaps insurmountable, obstacle. The fourth approach asks a different question entirely. What if we do not need to travel physically? What if we could simply observe the edge of the observable universe in ever greater detail, extending our senses rather than our bodies? This is, in a sense, what we already do. Every telescope is a time machine. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, when the light left it. The further we look, the further back in time we see. The Hubble Space Telescope, launched in 1990 and still operating after more than 3 decades in orbit, has allowed us to see galaxies as they existed more than 13 billion years ago, when the universe was only a few 100 million years old and the first structures were just beginning to form. The James Webb Space Telescope has pushed even further, detecting light from galaxies that existed when the universe was barely 200 million years old. Galaxies so young and so distant that their light has been travelling toward us for more than 13.5 billion years. In a sense, we have already reached the edge of the observable universe through observation. We have captured its light, we have measured its temperature, we have mapped its structure. The cosmic microwave background, that faint afterglow of the Big Bang, is the most distant thing we can detect, and we have studied it in exquisite detail. We know its temperature to 5 decimal places. We know its fluctuations to 1 part in 100,000. We know its polarization pattern, which carries information about the earliest moments of cosmic history. But observation is not presence. Seeing the edge is not the same as reaching it. The light we detect carries information about what the edge looked like billions of years ago, but it tells us nothing about what it is like now. The matter that emitted the cosmic microwave background has evolved for 13.8 billion years since those photons departed. Stars have formed and died in that matter. Galaxies have assembled, collided, and merged. Heavy elements have been forged in supernova explosions and spread through interstellar space. Planets may have formed. Life may have arisen. Civilizations may have risen and fallen, asked the same questions we ask, looked at their own cosmic microwave background from the opposite direction, and wondered what lay beyond their own horizons. We will never know, because we will never receive any updated information from that matter. The photons we captured are the last ones. No new photons from those regions will ever reach us. The message was sent once, long ago, and there will be no follow-up. There is a poignant quality to this observation. We are looking at the baby pictures of a universe that has long since grown up, and we will never see the adult it became. The CMB is like a photograph of a newborn taken at the hospital. The child is now 13.8 billion years old. It has lived an unimaginably long life. But we only have the baby picture, and we always will. There are proposals to extend our observational reach using forms of radiation other than light. Gravitational waves, ripples in the fabric of spacetime caused by accelerating masses, could carry information from epochs even earlier than the CMB. The LIGO observatories, which first detected gravitational waves on September 14, 2015, from the merger of 2 black holes, roughly 1.3 billion light-years away, have opened an entirely new window on the cosmos. LIGO consists of 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana, each consisting of 2 perpendicular arms, 4 kilometers long. Laser beams bounce between mirrors at the ends of the arms, and the passage of a gravitational wave causes one arm to stretch slightly while the other contracts, changing the interference pattern of the laser light. The sensitivity is extraordinary. LIGO can detect changes in arm length smaller than 1/10,000th the diameter of a proton. The Virgo detector in Italy, the Kagra detector in Japan, and the proposed Einstein telescope in Europe and Cosmic Explorer in the United States will further expand our gravitational wave detection capabilities. These instruments will be able to detect merging black holes and neutron stars at cosmological distances, providing a new map of the universe that is complementary to but different from what electromagnetic radiation reveals. The proposed LISA mission, the Laser Interferometer Space Antenna, is even more ambitious. LISA would consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers connected by laser beams. It would be sensitive to gravitational waves at much lower frequencies than LIGO, allowing it to detect different types of sources, including merging supermassive black holes at the centers of distant galaxies, compact binary star systems in our own galaxy, and potentially the gravitational wave background from the earliest moments of cosmic history. If inflation occurred, it would have generated a background of gravitational waves that permeates all of space, analogous to the cosmic microwave background, but carrying information from an even earlier epoch, perhaps the first 10 to the negative 32 seconds after the Big Bang, long before the universe was transparent to light. Neutrinos offer another avenue. These ghostly particles interact so weakly with matter that they can escape from environments that trap light. The Sun, for example, produces vast quantities of neutrinos in its core, and they pass through the Sun's outer layers as if they were not there. The cosmic neutrino background, analogous to the cosmic microwave background but composed of neutrinos instead of photons, was released approximately 1 second after the Big Bang, much earlier than the CMB. Detecting these ancient neutrinos would give us a snapshot of the universe at an even earlier stage, when it was a seething soup of particles and radiation, before even atoms had formed. However, the cosmic neutrino background has never been directly detected because the neutrinos have cooled to such low energies, roughly 1.95 degrees Kelvin, that they are extraordinarily difficult to observe. Current neutrino detectors are millions of times too insensitive to detect them. Proposed experiments like Ptolemy aim to push detection limits closer to the required sensitivity, but the technological challenges are enormous. There is also the tantalizing possibility of detecting primordial gravitational waves through their imprint on the cosmic microwave background. Gravitational waves from the inflationary epoch would have left a subtle pattern in the polarization of the CMB, a pattern called B-mode polarization. The BICEP and Keck array experiments at the South Pole have been searching for this signal for years. In 2014, the BICEP-2 team announced the detection of B-mode polarization, which was initially hailed as direct evidence of inflation. But further analysis revealed that the signal was contaminated by dust in our own galaxy. The true primordial signal, if it exists, remains below current detection limits. Future experiments, including the Simons Observatory and CMB Stage 4, may finally have the sensitivity to detect or rule out this signal, providing either confirmation or constraint of inflationary theory. But even these exotic probes have fundamental limits. Gravitational waves and neutrinos travel at or very near the speed of light. They cannot extend the particle horizon. They can tell us about different aspects of the cosmic history within the observable volume, but they cannot tell us about regions beyond the observable universe. The particle horizon is defined by the maximum distance any signal could have traveled since the Big Bang, regardless of the type of signal. No form of radiation or particle that travels at or below the speed of light can extend this horizon. And so the fourth approach ultimately fails. Observation cannot substitute for travel, no matter how sensitive our instruments become. No matter what forms of radiation we learn to detect, we will always be confined to the same bubble. The observable universe, that 93 billion light-year sphere, is all we will ever see. The rest, however vast, however rich, however full of wonders, is permanently hidden behind a horizon that no technology can pierce. The fifth and final approach is perhaps the most radical and the most speculative. What about exploiting the geometry of space-time itself? What about wormholes? Wormholes are hypothetical tunnels through space-time, connecting two distant points via a shortcut through a higher dimensional structure. They were first described mathematically by Albert Einstein and Nathan Rosen in 1935 as a consequence of the equations of general relativity. The Einstein-Rosen bridge, as it was originally called, emerged from the mathematics of black holes. It showed that the singularity at the center of a black hole could, in theory, connect to another singularity in a different region of spacetime, creating a passage that bypasses the intervening space entirely. In principle, a wormhole could connect 2 points separated by billions of light-years, while the wormhole throat itself might be only a few meters long. A traveler entering one end would emerge from the other almost instantly, regardless of the distance between the endpoints in normal space. This would not violate the speed of light because the traveler is not moving through normal space. They are taking a shortcut through the deeper geometry of spacetime, bypassing the intervening distance rather than crossing it. The concept is elegant. The execution is, to put it mildly, problematic. The first and most fundamental problem is that all known solutions for traversable wormholes require exotic matter with negative energy density, the same requirement as the Alcubierre warp drive. Without exotic matter to hold the wormhole open, the throat collapses before anything can pass through it. The gravitational tidal forces inside a collapsing wormhole would tear apart any matter that entered, stretching it into infinitely thin threads in a process called spaghettification. A wormhole without exotic matter is a death trap, not a transit system. The second problem is that there is no known mechanism for creating a wormhole. Wormholes might exist naturally as remnants of the extreme conditions of the Big Bang, or as quantum fluctuations in spacetime at the Planck scale, roughly 10 to the negative 35 meters. But these would be inconceivably small, smaller than a proton by a factor of roughly 10 to the 20th, and there is no known way to enlarge them to macroscopic size. The third problem is perhaps the most devastating for our purposes. Even if a traversable wormhole could be created and stabilized, connecting it to a specific distant location would require placing one end of the wormhole at that location first. To build a wormhole connecting our solar system to the edge of the observable universe, you would need to transport one end of the wormhole to the edge of the observable universe, which means you would need to make the journey we have been discussing. The shortcut presupposes a journey that cannot be made. It is like trying to build a bridge to an island by first swimming to the island with the bridge materials. If you could swim to the island, you would not need the bridge. And Kip Thorne, the Nobel Prize-winning physicist at Caltech who did groundbreaking work on both gravitational waves and traversable wormholes in the late 1980s, explored these ideas in detail. Thorne acknowledged that while the mathematics of general relativity permits traversable wormholes, the physical requirements are so extreme and so speculative that they may never be achievable. The exotic matter needed, the energy densities required, the stability conditions that must be maintained, all of these push the concept to the very edge of physical possibility and perhaps beyond it. There are additional concerns about stability. Many physicists believe that traversable wormholes, even if they could somehow be created and stabilized with exotic matter, would be inherently unstable against perturbations. Any matter or radiation entering the wormhole would create feedback effects, amplifying quantum fluctuations in the throat, which could trigger a runaway collapse. The wormhole would slam shut before anything useful could pass through. This instability has been studied by several groups and remains an active area of theoretical research, but no solution to the problem has been found that does not invoke even more exotic and speculative physics. In recent years, a fascinating theoretical connection has emerged between wormholes and quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a bold conjecture known as ER equals EPR, suggesting that quantum entanglement between particles, the phenomenon Einstein called spooky action at a distance, might be equivalent to tiny wormholes in spacetime. If true, this would mean that entangled particles are connected by microscopic Einstein-Rosen bridges. But these quantum wormholes are not traversable. They do not allow matter or information to pass through. They are more like a shared quantum property than a physical tunnel. The ER equals EPR conjecture is a beautiful theoretical idea, but it offers no practical route to faster-than-light travel or to reaching the edge of the observable universe. There is one more variation worth mentioning. Some physicists have speculated about the possibility of naturally occurring wormholes at the centers of certain black holes. The Kerr metric, which describes a rotating black hole, contains solutions that appear to connect to other regions of spacetime through an interior passage. But these mathematical solutions are generally regarded as physically unrealistic. The interiors of real black holes are almost certainly nothing like the idealized Kerr solution. Quantum gravity effects, which become important near the singularity, would likely destroy any traversable structure. And even if a passage existed, falling into a black hole to find it would mean crossing the event horizon, a one-way trip from which no return is possible and no information can be sent back. So where does this leave us? We have examined 5 approaches, spanning the full range from existing technology to the most speculative concepts in theoretical physics. Chemical and conventional propulsion fails by a factor of trillions. Relativistic travel, even at 99.99% of the speed of light, cannot outrun the expansion of space. Warp drives require exotic matter in quantities that may not exist, face unsolved stability problems, and create causality paradoxes. Observation extends our knowledge, but not our reach. And wormholes, if they exist at all, cannot be created, stabilized, or connected to destinations we cannot already reach. Every approach leads to the same conclusion, arrived at from a different direction, through different physics, with different mathematics, but converging on the same inescapable result. The edge of the observable universe is not merely far away, it is fundamentally, physically, mathematically unreachable. The laws of physics as we understand them do not merely make the journey difficult, they make it impossible. There is no known loophole, no clever trick, no exploit in the equations, no hidden doorway in the geometry of spacetime that could circumvent the expansion of space at the scale of the observable universe. It is worth pausing to acknowledge the emotional weight of this conclusion. Human beings are explorers. Our history is a chronicle of reaching places we were told were unreachable. We crossed oceans. We climbed mountains. We walked on the moon. The idea that there exists a frontier that we can never, even in principle, cross is alien to our nature. It challenges something deep in our sense of possibility, something hardwired into our psychology as a species that has always found a way. Every previous barrier has eventually fallen, but this one will not. It is not a barrier of technology or knowledge. It is a barrier of physics, embedded in the structure of reality, woven into the geometry of spacetime by the same equations that allow matter to exist and stars to shine. There is a temptation, when confronted with such absolute limits, to invoke future physics, to say that perhaps we will discover new laws that circumvent the ones we know. Perhaps quantum gravity will reveal hidden dimensions. Perhaps string theory will provide escape routes through the landscape of the multiverse. Perhaps something entirely unexpected will emerge, and perhaps it will. Physics is not finished. Our understanding is incomplete, but every piece of evidence we currently possess points in the same direction. The expansion is real. The acceleration is real. The horizons are real. And no known or plausible extension of physics removes them. And this leads to a deeper question, one that transcends physics and enters the realm of philosophy. If the edge of the observable universe is permanently unreachable, then what exactly is the observable universe? Is it a prison? A refuge? A finite window into an infinite reality? And what does it mean that this window is slowly, irrevocably closing? The deeper truth is not about distance. It is not even about speed, or expansion, or dark energy, though all of these play their part. The deeper truth is about time and loss, and the fundamental architecture of reality. The universe is not merely large and expanding. It is structured in such a way that most of what exists will be forever beyond our knowledge, and the fraction that we can know is shrinking with every passing moment. This is not a temporary condition. It is the permanent state of affairs in a cosmos dominated by dark energy. Let us trace this idea carefully, because it has implications that reach far beyond physics. Right now, in the early decades of the 21st century, we live in what cosmologists have called a privileged era. Not privileged in the sense that we are special, but privileged in the sense that we happen to exist at a time when the universe is still legible. The universe is old enough that complex structures, galaxies, stars, planets, and life have had time to form through billions of years of gravitational assembly and stellar nucleosynthesis. But it is young enough that we can still see the evidence of the Big Bang in the cosmic microwave background. We can still observe distant galaxies. We can still detect the acceleration of expansion. We can still read the story of the cosmos in the light that reaches our instruments. Future civilizations, billions or trillions of years from now, will not have these advantages. The evidence is disappearing. It is being erased, not by any malicious force, but by the same expansion that we have been discussing throughout this journey. As the expansion accelerates, driven by dark energy, galaxies beyond our local group will be carried past the event horizon, one by one. Their light will redshift. First, it will shift from visible wavelengths to infrared, then from infrared to microwave, then from microwave to radio wavelengths, so long that no conceivable antenna could detect them. Their images will dim, blur, and vanish. From the perspective of a civilization living in the far future, the sky will be almost empty. The only galaxies visible will be those bound to our own by gravity, a small cluster of perhaps 50 or 60 galaxies, dominated by the merged remnant of the Milky Way and Andromeda, which will collide and merge in approximately 4.5 billion years, forming a single giant elliptical galaxy that some astronomers have nicknamed Milky. Let that sink in. A civilization born in that era, trillions of years from now, would look up at a sky containing a single galaxy surrounded by perfect, utter, unbroken darkness. They would have no external reference points, no distant galaxies to observe, no redshifts to measure, no evidence of expansion. They would look out in every direction and see nothing but empty space, stretching to infinity. And they would draw conclusions from this emptiness that would be entirely reasonable, given their evidence, and entirely wrong. They would conclude, quite logically, that the universe consists of a single galaxy floating in an infinite, static void. They would have no evidence that the universe was ever different. The cosmic microwave background, which currently tells us so much about the Big Bang and the early universe, would have been redshifted beyond detection. At a cosmic age of 100 billion years, the CMB would have a temperature of roughly 0.3 degrees Kelvin. At a trillion years, it would be below 10 to the negative 10 degrees Kelvin. At 10 trillion years, essentially zero, undetectable by any instrument that obeys the laws of thermodynamics. The afterglow of creation would have faded below the noise floor of the universe itself. Without the CMB, without distant galaxies, without the ability to measure expansion, that future civilization would have no way to deduce the Big Bang. They would have no evidence of a hot, dense origin. No evidence that the universe had been smaller, hotter, denser in the past. No evidence that it was expanding, let alone accelerating. Their cosmology would be fundamentally, profoundly wrong. Not because they lacked intelligence or curiosity or scientific rigor, but because the evidence would have been destroyed by the passage of time and the stretching of space. This extraordinary idea was explored in detail in a paper published in 2007 by Lawrence Krauss of Arizona State University and Robert Scherer of Vanderbilt University, titled The Return of a Static Universe and the End of Cosmology. They argued, with meticulous calculations, that future observers would live in a universe that is, for all practical purposes, indistinguishable from the static, eternal cosmos that scientists believed in before Hubble's discovery. Einstein's original assumption, the one he later called his greatest blunder, would appear to be vindicated. The cosmological constant that he introduced to prevent expansion would seem unnecessary because expansion would be undetectable. The universe would have hidden its own nature. This is not a distant concern. It is already happening. Right now, at this moment, galaxies are crossing the event horizon. Their light is being stretched into oblivion. The information they carry about the large-scale structure of the cosmos, about the distribution of matter, about the expansion history, is being erased. Every second, the volume of the universe that we can interact with grows smaller relative to the total volume of the cosmos. We are losing access to reality, and we will never get it back. Let that sink in. We live in a brief window of cosmic history, during which the universe is still young enough, still transparent enough, still compact enough, for us to understand what it is. That window will not last. The evidence is already fading. The light is already stretching. The galaxies are already vanishing. This gives a new dimension to our original question. How long would it take to reach the edge of the observable universe? The answer, properly stated, is that the question itself is malformed. The edge of the observable universe is not a destination, it is a horizon. Like the horizon on Earth, it is defined by the observer's position and the geometry of the space around them, not by any physical feature of the landscape. If you move forward on Earth, the horizon moves with you. But unlike the earthly horizon, the cosmic horizon is also receding due to expansion. It is a moving target that moves faster than you can chase it. Walking toward the horizon does not bring you closer to it. It brings new ground into view while old ground vanishes behind you. And in the cosmic case, even new ground stops appearing eventually, because the expansion accelerates. There is a thought experiment that clarifies this further. Imagine you are standing on a vast, flat plain, and the horizon is 10 kilometers away. You begin walking toward it. As you walk, the horizon recedes at exactly the same pace you advance. After walking 10 kilometers, the horizon is still 10 kilometers away. You have not gotten closer. You have simply moved. Now imagine that the plain is stretching, like a rubber sheet being pulled from the edges. As you walk forward, the ground beneath your feet is also stretching, carrying objects behind you further away and pushing the horizon ahead of you even faster. Now the horizon is not merely keeping pace with your walking, it is receding faster than you can walk. After 10 kilometers of walking, the horizon is 15 kilometers away. After 20 kilometers, it is 30. The faster you walk, the faster the plain stretches, and the further the horizon retreats. This is the cosmic situation. The plain is space. The stretching is the expansion. The horizon is the edge of the observable universe. And the speed limit on your walking is the speed of light. Even if we reframe the question as how long would it take to reach the matter that currently defines the edge of the observable universe, the answer is still infinity. That matter is currently 46.5 billion light-years away and receding at roughly 3 times the speed of light. No finite journey can reach it. No finite time will suffice. The journey is not long. It is impossible. These are different things, and the difference matters. A long journey can be shortened with better technology. An impossible journey cannot. The distinction is not one of degree, it is one of kind. There is yet another way to feel the weight of this impossibility. Consider the concept of the cosmic light horizon. Every photon that will ever reach us from the cosmos has already been emitted. Every photon that will ever enter our past light cone is already on its way. The number of photons we will ever receive from the universe is finite and fixed. We cannot increase it. We cannot add to it by building better telescopes or by waiting longer. The total information content of the observable universe, from our perspective, is bounded. It has a maximum. And that maximum is determined by the size of the observable universe, the finite age of the cosmos, and the accelerating expansion that prevents new signals from entering our horizon. This means that our understanding of the universe has a ceiling. There is a maximum amount of knowledge we can ever possess about the cosmos. We will approach that ceiling asymptotically, building better instruments, detecting fainter signals, extracting more information from the light we have already received, but we will never exceed it. The universe has given us a finite amount of data, and no amount of cleverness can extract more than the data contains. We are limited not by our minds, but by the universe's willingness to communicate. The cosmos has told us its story, or at least a fragment of it, and then it has turned away. The rest of the story will be told in places we can never reach, in languages we can never learn, to audiences we can never meet. What we have received is a gift, a brief, brilliant, once-in-an-eternity transmission from the edge of all things, and it is fading even as we decode it. But there is an even deeper layer to this truth. The unreachability of the cosmic edge is not an anomaly. It is the rule. Most of the universe has always been beyond our reach. Even in the earliest moments of the Big Bang, regions of space that are now visible to us were too far apart to communicate with each other. This is the origin of what cosmologists call the horizon problem. The cosmic microwave background is astonishingly uniform in temperature, varying by only about 1 part in 100,000 across the entire sky. The temperature at one point on the CMB is nearly identical to the temperature at a point on the opposite side of the sky, 46 billion light-years away in the other direction. But those 2 points were never in causal contact. They were always too far apart for light, or any signal, to travel between them in the time available since the Big Bang. How did they reach the same temperature? The leading explanation is cosmic inflation, a theory proposed by Alan Guth of MIT in 1980. Inflation suggests that in the first fraction of a second after the Big Bang, roughly from 10 to the negative 36 seconds to 10 to the negative 32nd seconds after the initial singularity, the universe underwent a period of exponential expansion that dwarfs anything that has happened since. Space expanded by a factor of at least 10 to the 26th, perhaps much more, in a time span shorter than the blink of an eye, shorter than any interval of time that has any intuitive meaning for human beings. This expansion was driven by a hypothetical field called the inflaton field, which filled space with an enormous energy density that drove the expansion at a rate far exceeding anything dark energy produces today. To appreciate the scale of inflation, consider this. Before inflation began, the region of space that would eventually become our entire observable universe was smaller than a proton. In a fraction of a second, it was stretched to a size that dwarfs anything we can currently observe. If you could have watched inflation happen, which you could not, because it happened far too quickly and the universe was opaque at the time, you would have seen space itself exploding outward at rates that make the current accelerating expansion look like a gentle drift. During inflation, the doubling time of the universe was roughly 10 to the negative 37 seconds. In that incomprehensibly brief interval, the size of the universe doubled, then doubled again, and again, and again. Roughly 80 to 90 doublings occurred, each one in less time than it takes a photon to cross the nucleus of an atom. The evidence for inflation comes from multiple independent lines of observation. The flatness of space, as measured by the Planck satellite to within 0.4%, is explained naturally by inflation, which stretches any initial curvature to near flatness, just as inflating a balloon makes its surface appear flat to an ant standing on it. The uniformity of the CMB is explained by inflation, as described earlier. The slight density fluctuations in the CMB, which seeded the formation of all cosmic structure, have precisely the statistical properties that inflationary models predict: a nearly scale-invariant spectrum with a slight tilt, and the absence of magnetic monopoles, exotic particles, predicted by grand unified theories that should have been produced abundantly in the early universe, is explained by inflation diluting them to undetectable concentrations. During inflation, a tiny region of space, perhaps smaller than a proton, was stretched to a size larger than the observable universe we see today. Regions that had been in causal contact before inflation, that had exchanged energy and reached thermal equilibrium, were suddenly ripped apart and carried far beyond each other's horizons. This explains the uniformity of the CMB. The temperature is the same everywhere, because, before inflation, the regions that produced the CMB were close enough to reach equilibrium. Inflation then stretched them apart, preserving the uniformity while making the regions causally disconnected. If inflation is correct, and nearly all cosmological evidence supports it, then the total universe is not just larger than the observable universe. It is incomprehensibly, staggeringly, almost meaninglessly larger. The observable universe, vast as it is a vanishingly small fraction of the whole. Some estimates suggest that if the observable universe is the size of a proton, the total universe could be larger than the current observable universe. The ratio is so extreme that it defies numerical expression. It is not that the total universe is 1,000 times larger, or 1,000,000 times, or 1,000,000,000 times. It is that the total universe could be 10 to the power of some enormous number times larger. The numbers become towers of exponents that have no referent in physical experience. This means that everything we have ever seen, every galaxy and every deep field image, every photon of the cosmic microwave background, every gravitational wave from every merging black hole, comes from a region that represents an almost infinitesimally small patch of the total cosmos. We are not exploring the universe. We are peering through a keyhole. And the room beyond the door is larger than anything the human mind can construct, larger than any analogy can convey, larger, perhaps, than any number can express. This is not science fiction. This is the standard, consensus model of modern cosmology, supported by decades of observation, confirmed by satellite measurements of the CMB, consistent with the most fundamental theories of particle physics and general relativity. The universe is mostly unknowable, not because we lack the tools, not because we need better technology, but because the structure of spacetime itself forbids it. The laws of physics that allow us to exist are the same laws that limit what we can know. The fire that warms us also walls us in. Consider one more unsettling implication of this vastness. If the universe is truly enormous, perhaps infinite, and if the laws of physics are the same everywhere, as all evidence suggests, then probability becomes a strange and troubling force. In an infinite universe, every possible arrangement of matter, no matter how improbable, occurs somewhere. There could be other worlds identical to Earth, other civilizations identical to ours, other beings asking the same questions we ask, looking at the same stars we see, though from slightly different angles. In an infinite universe, these copies are not just possible, they are mathematically inevitable, and we will never know they exist. We will never meet them. We will never confirm or deny their presence. They are out there, perhaps, in the mathematical sense, but they are not out there in any physical sense that matters to us. The Fermi paradox, the question of why we have not detected signs of intelligent life in our cosmic neighborhood, despite the vast number of potentially habitable worlds, takes on a new dimension in this context. Perhaps life is common throughout the cosmos. Perhaps intelligence arises frequently. Perhaps there are billions of civilizations scattered through the 2 trillion galaxies of the observable universe alone. But the distances between stars, between galaxies, between galaxy clusters are so enormous, and the expansion is so relentless, that each civilization is effectively alone. Not because life is rare, but because the cosmos is structured to keep its inhabitants apart. The silence is not evidence of absence. It may be evidence of architecture. The loneliness we feel when we look at the stars may not be the loneliness of a rare species in a barren universe. It may be the loneliness of one of countless species in a universe that is simply too large, too fast, and too indifferent for any of them to find each other. There is a further consequence of the accelerating expansion that deepens the melancholy of this picture. The universe is not merely isolating its inhabitants from each other. It is heading toward a state that physicists call the heat death. In thermodynamics, every closed system tends toward a state of maximum entropy, a state in which energy is spread out as evenly as possible, where no useful work can be done, where all temperatures have equalized, and where nothing happens. The universe is the ultimate closed system, and the accelerating expansion is hastening its approach to maximum entropy. In the far future, all the stars will burn out. The last red dwarfs, the most frugal and long-lived stars, will exhaust their hydrogen fuel roughly 10 trillion years from now. After that, the universe will be lit only by the slow decay of stellar remnants. White dwarfs will gradually cool over trillions of years, fading from hot white to dull red to invisible black. Neutron stars will spin down and cool. Black holes will slowly evaporate through Hawking radiation, a process predicted by Stephen Hawking in 1974, in which quantum effects near the event horizon cause black holes to emit particles and gradually lose mass. The largest supermassive black holes containing billions of solar masses will take roughly 10 to the 100th years to evaporate completely. That number is a 1 followed by 100 zeros. It is so far in the future that it makes the current age of the universe seem like the opening frame of an unimaginably long film. After the last black hole evaporates, the universe will consist of nothing but a thin, cooling gas of photons, neutrinos, and the occasional electron or positron, all drifting apart at ever-increasing speeds, with the temperature approaching but never quite reaching absolute zero. This is the heat death. It is not violent, it is not dramatic. It is simply the end of all complexity, all structure, all process. The universe will become a uniform, featureless void, expanding forever, cooling forever, with nothing happening and nothing left to happen. Against this backdrop, the question of reaching the edge of the observable universe takes on an existential dimension. We exist in a brief epoch of cosmic history, a window of roughly 10 trillion years during which stars shine and complexity is possible. Sandwiched between the violent birth of the Big Bang and the infinite cold emptiness of the heat death, within this window, we have an even briefer sub-window during which the universe is still legible, during which the CMB is still detectable, and the galaxies are still visible. That sub-window is perhaps 100 billion years long, and within that sub-window we have appeared, grown curious, built telescopes, and begun to ask how far the cosmos extends. Our timing is extraordinary. A little earlier, and the conditions for complex life would not have existed. A little later, and the evidence of the Big Bang would have been erased. We have arrived at precisely the right moment to understand the universe's story, a story that will soon become untellable. There is one more layer of depth to explore before we move on. The concept of the multiverse, while speculative, adds yet another perspective on the unreachability of the cosmic edge. If inflation is correct, and if the inflaton field that drove it could take different values in different regions, then different parts of the universe may have inflated at different rates, creating separate pocket universes within a larger inflationary multiverse. Each pocket universe would have its own observable horizon, its own expansion rate, and potentially its own fundamental constants. The laws of physics might vary from one pocket to another. The mass of the electron, the strength of gravity, the cosmological constant, all of these could be different in other pockets. If this picture is correct, then our observable universe is not just a small part of a larger universe. It is one of an essentially infinite number of separate pocket universes, each one permanently disconnected from every other, each one expanding into its own future, each one containing its own horizons and its own impossibilities. The physicist Max Tegmark has categorized different levels of multiverse theories, from the relatively conservative Level 1 multiverse, in which the universe is simply larger than what we can observe and contains all possible initial conditions, to the more radical Level 4 multiverse, in which all mathematically self-consistent structures have physical existence. At every level, the fundamental theme is the same. The reality we can observe is a tiny, perhaps infinitesimally small, fraction of what exists, and the rest is not merely unknown, it is unknowable, not because we have failed to look hard enough, but because the structure of reality prevents us from looking further. This brings us full circle to the question of meaning. What does it mean to exist inside a bubble of visibility in a cosmos that may be infinite? What does it mean to know that we can never know most of what is? Some find this liberating. The unknowable universe places no demands on us. We are free from the obligation to map the entire cosmos, to catalogue every galaxy, to reach every star. Others find it diminishing. The vastness makes us small, and the unknowability makes us blind. We are limited creatures in a limitless reality, able to see only a fraction of a fraction, reaching for edges that recede at the speed of reality itself. But there is a third response, and it is perhaps the most honest. We can hold both the wonder and the limitation simultaneously. We can be awed by what we can see and humbled by what we cannot. We can study the cosmic microwave background with exquisite precision, knowing that it is only the innermost surface of a mystery that stretches beyond all horizons. We can build telescopes that peer across billions of light years, knowing that beyond the reach of the most powerful instrument, the universe continues without us, perhaps forever. We can be grateful for the brief window of clarity in which we exist, knowing that it will close. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We have emerged on one small world, orbiting one ordinary star in one of 2 trillion galaxies, inside a bubble of visibility that represents an almost vanishingly small fraction of what exists. And the bubble is shrinking. The view is fading. The cosmic night is closing in, slowly but inexorably, and there is nothing we can do to stop it. The journey to the edge of the observable universe is not a journey measured in years or kilometers. It is a journey measured in impossibility. The universe has placed a boundary around us, not of walls or barriers, but of physics itself, of the speed of light and the relentless expansion of space and the remorseless acceleration of dark energy. We live inside that boundary. We think inside it. We dream inside it. We ask our questions inside it. And we will die inside it. Every human who has ever lived, and every human who will ever live, will exist within this bubble. It is the only home our species will ever have, not because we lack ambition, but because the universe lacks a path. And there is a strange irony embedded in this limitation. The same expansion that imprisons us is also what allows us to exist. Without the expansion, the universe would have collapsed back on itself long ago under its own gravity, or remained a hot, dense plasma forever, unable to cool enough for atoms to form, or burned through all its nuclear fuel in an instant, leaving nothing but radiation and exhausted particles. The expansion is what cooled the universe enough for atoms to form, for stars to ignite, for planets to condense from clouds of gas and dust, for chemistry to become biology, for biology to become thought, for thought to become wonder. The same force that keeps us from reaching the edge is the force that made us possible. We are products of the process that limits us, children of the expansion, trapped by our own parent. But perhaps there is a strange beauty in that. Perhaps the very impossibility of the journey is what gives it meaning. We are creatures who ask questions we can never answer, who reach for destinations we can never touch, who look at the sky and feel the pull of distances we can never cross. That impulse, that yearning toward the unreachable, is not a flaw. It is perhaps the most remarkable thing about us. In a universe that appears to have no purpose, we are the part that invents purpose. In a cosmos that has no opinions, we are the part that forms them. We are the universe's way of knowing that it has edges, even if we can never visit them. What does it mean to live in a universe you can never fully explore? What does it mean to know that most of reality is, and will always be, hidden from you? What does it mean to be a conscious being in a cosmos that is overwhelmingly unconscious, overwhelmingly empty, overwhelmingly indifferent to whether you exist? These are not questions that physics can answer. Physics can tell us the expansion rate of the universe with great precision. It can calculate the distances to the cosmic horizons. It can describe the curvature of spacetime and the properties of dark energy and the temperature of the cosmic microwave background to 5 decimal places. But it cannot tell us what those facts mean for the beings who discover them. That is a question for philosophy, for art, for the quiet hours before sleep when the mind turns inward and tries to find its place in the immensity. For most of human history, the universe seemed knowable. The sky was a dome of crystal. The stars were fixed points of light, perhaps pinholes in a cosmic canopy through which divine radiance shone. The earth was the center of everything, and the cosmos was built to human scale. It was a universe you could hold in your mind, a universe that had been made, presumably, for us. Every culture on Earth developed a cosmology that placed humanity at the center, or near the center, or at least within the notice of whatever forces governed the sky. The cosmos was cozy. It fit inside human imagination. Then Copernicus displaced us from the center. In 1543, he proposed that the Earth orbited the Sun, not the other way around. This was not merely a change in astronomical models. It was a philosophical earthquake. If the Earth was not the center of the universe, then perhaps humanity was not the point of the universe. Perhaps we were peripheral. Perhaps we were incidental. The centuries that followed only deepened the displacement. Galileo showed us the moons of Jupiter and the phases of Venus, proving that not everything orbited the Earth. Newton gave us gravity, a universal force that governed the motion of planets and apples alike, with no special place for human beings. Darwin showed us that we were not separate from nature but a product of it, shaped by the same blind forces that shaped every other living thing. And then Hubble showed us the expanding cosmos. The universe was not static. It was not eternal and unchanging. It had a beginning. It was growing. and it was far, far larger than anyone had imagined. Each discovery made us smaller, not in stature, not in dignity, not in moral worth, but in cosmic proportion. We are not at the center of the solar system. We are not at the center of the galaxy. We are not at the center of the universe. There is no center. The universe has no edges, no preferred location, no special point. Every point is equivalent to every other point. We are nowhere in particular. This process of displacement, which the philosopher Dennis Danielson has called the Copernican myth, is often told as a story of humiliation, a story in which humanity is repeatedly knocked off its pedestal. But it can also be told differently. Each displacement was also a discovery. Each step away from the center was also a step toward understanding. We lost our privileged position, but we gained something greater. We gained knowledge. We gained the ability to see the universe as it actually is, not as we wished it to be. And what we see, when we look honestly, is breathtaking. The universe is not built for us, but it is built, and we can understand how. That understanding is its own form of significance, perhaps the deepest form. Consider what we have accomplished in our brief tenure on this planet. We have measured the distance to the edge of the observable universe to within a few percent. We have determined the age of the cosmos to within 21 million years. We have mapped the distribution of matter in the early universe when it was only 380,000 years old. We have detected gravitational waves from colliding black holes billions of light years away. We have discovered that the expansion of the universe is accelerating and that most of the cosmos is made of substances we cannot see or touch. We have done all of this from the surface of a single small world, using instruments made of the same atoms that were forged in the cores of ancient stars. The fact that stardust can know itself, can measure the cosmos that created it, can understand the forces that will eventually destroy it, is perhaps the most improbable and beautiful thing in the entire observable universe. And yet we are the part of the universe that asks questions. We are the atoms that learn to think. We are the cosmos examining itself, turning its attention inward, trying to understand its own structure, its own history, its own fate. There is something profound in that, something that resists the diminishment of scale. However small we are in physical terms, however brief our existence in cosmic time, we are the part of reality that is aware of itself. And in an overwhelmingly unconscious universe, consciousness is rare. Perhaps vanishingly rare, perhaps unique, though we have no way to know. But even if consciousness is common throughout the cosmos, even if billions of civilizations have arisen and flourished in the observable universe, each one is isolated by the same expansion that isolates us. Each one is locked inside its own horizon. Each one is asking the same questions into the same cosmic silence, and none of them can hear each other. Two. The astronomer Carl Sagan once reflected on a photograph of Earth taken by the Voyager 1 spacecraft from a distance of roughly 6 billion kilometers, a photograph he had personally advocated for. In that image, Earth appears as a tiny speck of light, less than a single pixel wide, caught in a scattered beam of sunlight. Sagan observed that every person who had ever lived, every ruler and subject, every saint and sinner, every creator and destroyer of civilization, had lived out their lives on that barely visible mote. The photograph did not make humanity seem grand. It made humanity seem fragile, temporary, and achingly small against the immensity of space. And the observable universe is 6 billion kilometers the way a raindrop is an ocean. The distances Sagan contemplated were trivial compared to the spans we have discussed throughout this journey. Voyager 1 is roughly 24 billion kilometers from Earth after nearly 50 years of travel. The edge of the observable universe is roughly 4.4 times 10 to the 26th power kilometers away. The ratio is about 18 trillion to 1. Voyager's Odyssey, which has taken nearly half a century, represents a distance so small relative to the observable universe that it barely registers on any scale. We have not even taken our first step. There is a philosophical concept sometimes called the cosmic perspective. It is the practice of viewing human concerns against the backdrop of the universe, of measuring our problems and achievements against the scale of galaxies and eons. Some people find this perspective liberating. If the universe is so vast and so indifferent, then our mistakes and our embarrassments are cosmically insignificant. Nothing we do matters on the scale of the cosmos. We are free from the weight of cosmic importance because we have none. Others find the same perspective terrifying for precisely the same reason. If nothing matters cosmically, does anything matter at all? But perhaps the most honest response is neither liberation nor terror. Perhaps it is simply wonder, held without resolution, without needing to be resolved. The fact that we exist at all, in a universe that is overwhelmingly hostile to life, is remarkable. The conditions required for the emergence of complex chemistry, stable stars, liquid water, and biological evolution are astonishingly narrow. The fact that we can contemplate the distances we have discussed tonight, can build telescopes that peer across billions of light years, can write equations that describe the expansion of space, can feel the pull of the unreachable, is extraordinary. We are not significant in the way we once imagined, as the centerpiece of a cosmic drama designed for our benefit, but we are significant in a different way. We are the universe's way of knowing itself, briefly and imperfectly, before the evidence fades and the darkness closes in. The journey to the edge of the observable universe will never be made. No spacecraft will ever attempt it. No traveler will ever complete it. No technology, however advanced, will ever make it possible. The laws of physics have spoken on this matter, and their verdict is final, but the journey has been made in a sense by our minds. We have travelled there, in mathematics, in theory, in imagination. We have calculated the distance, measured the expansion, mapped the horizons, and understood why the edge is forever beyond our reach. And that mental journey, that act of comprehension across incomprehensible distances, is itself a remarkable achievement. It is perhaps the most extraordinary voyage any species has ever undertaken, a journey not through space but through understanding, a crossing not of light years but of ignorance. The expansion continues, the galaxies recede, the cosmic microwave background fades imperceptibly toward oblivion, and we, on our small world, surrounded by our small concerns, look up at the night sky and try to understand the place we occupy in the immensity. We cannot reach the edge, but we can know it is there. And knowing perhaps is enough, or if not enough, then at least something real and hard-won and ours, a piece of truth extracted from the darkness by minds that had no reason to exist and no guarantee that they ever would. We live in a privileged moment, not privileged because we are special, but privileged because the universe is still visible, the CMB is still detectable, the distant galaxies still shine. The expansion is still measurable, the story of the cosmos is still readable in the light that fills the sky. Someday, far in the future, that story will be unreadable. The evidence will have faded. The galaxies will have vanished. The universe will have erased its own autobiography. And whatever beings exist in that distant era will have no way to know what we know now. They will look out at a single galaxy in an empty void and believe that is all there is. They will be wrong. But they will have no way to know they are wrong. Our knowledge, our understanding, our brief, bright glimpse of the truth is something that will not be available again. We are the witnesses, and our testimony, recorded in our equations and our instruments and our stories, may be the only record of the cosmos as it truly was. There is a particular quality of loneliness that comes from understanding the architecture of the cosmos. It is not the loneliness of being alone in a room or alone on a road at night. It is the loneliness of being alone in a cathedral so vast that the walls are beyond sight, the ceiling is beyond reach, and the echo of your voice never returns. The universe does not answer our questions. It does not acknowledge our presence. It simply expands, indifferent to whether anyone is watching, and yet we watch. We cannot help it. The desire to look up, to wonder, to reach, is woven into whatever we are. It is the engine that drives science, that fuels exploration, that compels us to ask questions we know we may never answer. Curiosity is its own justification. The desire to know is not diminished by the impossibility of knowing everything. If anything, it is sharpened by it. The edge of the observable universe is 46.5 billion light-years away. It is not a wall. It is not a boundary you can touch or see or approach. It is not marked by any physical structure, any cosmic landmark, any change in the laws of physics. It is a horizon, defined by the finite speed of light and the finite age of the cosmos. Beyond it, there is almost certainly more universe, perhaps infinitely more, stretching in directions and dimensions we cannot perceive, filled with galaxies and stars and perhaps civilizations that will never know we existed, but we will never see it, we will never reach it, we will never know what lies beyond. This is not a limitation of our technology. It is not a challenge to be overcome by future generations with better engines or bolder vision. It is a structural feature of the universe itself, as fundamental as gravity, as inescapable as the second law of thermodynamics. The expansion of space, driven by dark energy, ensures that the cosmic horizon will always recede faster than we can approach it. The speed of light, the fastest speed permitted by the laws of physics, is not fast enough. It will never be fast enough. The universe has set a speed limit and then built a racetrack that outgrows it, a track that stretches faster than the runners can run. We live inside a bubble of light, of information, of causal connection. Everything we know, everything we have ever detected, everything that has ever affected us or been affected by us, exists within this bubble. It is our cosmic home. It is the entirety of our past and the boundary of our future. Outside it, there is more, perhaps an infinity of more, but it is as inaccessible to us as the interior of a black hole, as remote as the moments before the Big Bang, as hidden as the far side of eternity. The journey to the edge of the observable universe, stated in plain terms, would take an infinite amount of time at the speed of light. Not a very long time. Not an astronomically long time. Infinite. The destination is receding faster than the traveller can approach it, and the acceleration of that recession ensures that no amount of waiting, no amount of travelling, no burst of speed, no feat of engineering will ever close the gap. In a universe governed by dark energy and described by general relativity, the edge of the observable universe is the definition of unreachable. It is unreachable in the way that the past is unreachable, not because the road is long, but because the road does not exist. And yet the question was worth asking, because in asking it, we have learned something extraordinary about where we are. We have learned that we live in a universe that is 93 billion light-years across and still growing, a universe that contains at least 2 trillion galaxies and 700 sextillion stars, a universe that is 68% dark energy, 27% dark matter, and only 5% the kind of matter we can touch and see and be. A universe that began 13.8 billion years ago in a state of unimaginable density, a state we call the Big Bang, and that has been expanding and cooling and complexifying ever since. A universe that hides most of itself behind horizons that cannot be crossed, in distances that cannot be traversed, in expansions that cannot be outrun. We have learned that the cosmos is not a stage on which things happen. It is a dynamic, evolving, expanding entity, carrying its contents toward an ever greater isolation. The night sky, which seems so permanent, so crowded with light, is in fact a fleeting snapshot of a vanishing era. The galaxies are leaving. The CMB is fading. The evidence of the Big Bang is being erased by the same expansion that the Big Bang set in motion. The universe is writing its story in disappearing ink. The observable universe is our home. It is the only home our species will ever have. We cannot leave it. We cannot expand it. We can only explore the fraction of it that light can reach, and that fraction is diminishing with every passing moment. This is the human condition, viewed from the largest possible scale. We are finite creatures in a potentially infinite cosmos, granted a brief window of visibility before the lights go out. And within that window, we have done something remarkable. We have looked, we have measured, we have understood. We have taken the meager handful of photons that the universe has allowed to reach our instruments, and from them we have reconstructed the history of creation. We have inferred the existence of dark energy and dark matter from the motions of galaxies we can barely see. We have dated the universe to within 21 million years. We have mapped the temperature of the cosmic background radiation to 5 significant figures. We have done this with brains that evolved for finding fruit and avoiding predators, using tools made of silicon and glass and starlight. One day, all of this knowledge may be lost. The stars will burn out, the galaxies will merge and fade, the cosmic background will redshift into nothingness. Future civilizations, if any exist, will inherit a cosmos that has erased its own history. The night sky will be dark, the microwave background will be silent, the evidence of the Big Bang will be gone, and the universe will seem, to whoever is left to observe it, small and static and eternal, a single galaxy in an endless void, with no memory of the trillions of others that once filled the sky, no memory of the expansion, no memory of the acceleration, no memory of us. We are the generation that knows. We are the ones who can see the full picture, or at least as much of it as the universe will ever reveal. That knowledge is a privilege. It is also a burden, because once you understand how vast the cosmos is, once you grasp how much of it is forever beyond your reach, once you feel the weight of those distances and those timescales, the universe never looks quite the same again. The stars are not just beautiful, they are also impossibly far away. The night sky is not just serene, it is also slowly emptying. How the silence between the stars is not just quiet, it is the sound of distances too large to cross and expansions too fast to outrun. How long would it take to reach the edge of the observable universe? Forever. And that forever is not a figure of speech. It is not hyperbole. It is not a casual exaggeration used for dramatic effect. It is a mathematical certainty, derived from the equations of general relativity, confirmed by every cosmological observation we have made in the past century, sealed by the relentless acceleration of cosmic expansion. The edge is unreachable. It has always been unreachable, and in a universe driven by dark energy, it will remain unreachable for all of time, for all of existence, for as long as the cosmos persists in its current form. The stars are beautiful, the distances are terrifying, and the silence between them is the deepest silence there is. We look up, and we see light that has travelled for billions of years to reach our eyes. That light began its journey when the Earth did not yet exist, when the sun had not yet formed, when the atoms in our bodies were scattered across interstellar clouds. By the time it arrives, the source that emitted it has been carried far beyond our reach, a ghost of a galaxy that we will never visit, whose light is the only proof it ever was. We are looking at a memory, a cosmic memory, carried across billions of years by the thinnest possible thread of photons, arriving just in time for beings who happen to evolve just the right kind of eyes to see it. The universe does not owe us answers, it does not owe us access, it does not owe us understanding or meaning or companionship, it does not owe us anything at all, but it gave us eyes to see, and minds to wonder, and a brief, improbable, unrepeatable moment of awareness in which to ask the questions that matter most. That moment will not last. Nothing does. The expansion will continue. The darkness will deepen. The horizons will shrink. But while it lasts, while we are here, while the light still reaches us from the deep cosmos, it is enough to look up and to know that the edge of everything is out there, impossibly far, impossibly beautiful, and impossibly beyond reach, and to feel in that knowledge something that can only be called awe, the awe of a small mind comprehending a vast truth, the awe of stardust recognizing itself, the awe of a universe that grew eyes, looked out at its own immensity, and whispered, in a voice too quiet for anyone else to hear, "How far?"